Oh yeah, and we are live from the YouTube universe. Let me hit the intro, and here we go. Boom! All right, we are live. Let me go over here, head over Discord, and let's do this. We have already Rachie 50 and StingRay here. Check 1 2. Hey, I just kicked off the show. We are live in the YouTube universe, and I am so happy and glad that both of you are able to make it. It was kind of a spontaneous little plan. So thank you so much both for being here. StingRay, mic check. Hello, hello. Rachie 50, mic check. Hello, glad to hear you, glad to see you. Welcome to the Boom. It's the first time that you joined the channel. Hopefully it's not the last. Yeah, I see you in the chat box, so I guess you enjoy the show, enjoy the discussion also. If not, you were not here talking to us, right? I guess. Uh, Thank you very much. I really appreciate that. All right. Well, I see the screen. StingRay is sharing the screen. I'm gonna mute myself. I'm gonna share the screen, and you both have the floor. I don't think I'm gonna have to moderate whatsoever. If you need to share something specific, Rachie, let me know. StingRay, your screen will be up. I'll go mute. Boom.
About the moon and tides, and then I realised that the moon was 6.7 degrees off the equator, like when I googled it, and I just wondered how, if it's 6.7 degrees off the equator, how it could pretty much be near enough directly overhead for me right now in the UK, like.
Right. Okay. So in building this model, I had to learn a few things, and the things that are important to kind of visualize this are the tilt of the Earth, its relationship to the Sun, and then the ecliptic offset. So the in a straight line to the Sun, we're orbiting it, the offset of 5.14 degrees for the orbit of the Moon. Now, if you can see my screen, I've got the Earth here, and then this orange thing is actually the correct distance to the Moon, which is way out here. Now, the Moon out here is on a
Hold on 1 second.
Offset
StingRay.
of
do you know how to see his screen share, Rachie?
No, I'm looking at you at the minute.
Yeah, you click on over his name over here on the Discord app. You click on his name, and it's gonna give you an option to watch stream or watch live view or something like that. And then you click on that, and whatever he's presenting, you will see it in real time. If you're watching on YouTube, it's gonna be like 30 seconds lag behind. Just click on his name on Discord and watch the stream. There you go. Yeah, you got it. I'll go back on mute.
Yeah, I got it.
Cool. So, so this is set up as our solar system is. So this is a 5-point. Let's have a look at this. It's this arrow that is the offset. So it's a 5.14 degree offset of this orbit, which is what the moon does. And then we've got a 23.5 degree axial tilt of the Earth.
Yep.
Which is via this box here. Now, I happen to have also placed the camera observer in our amazing, beautiful area of this Earth in England. Doesn't actually, you know, doesn't matter whether it's within like 50 square miles or 100 square miles. The results are pretty much the same. Now, in order for us to figure out, well, what's the angle or what's the highest elevation relative to ourselves that the moon can be in, we first of all need to figure out, well, since the moon is near enough, you know, it's only got 5.1 whatever degrees off the ecliptic. What's the point when we're closest to or most, you know, the least tangent difference? And if I rotate this round here, can you see now that to ourselves, there's not that much angle to you know, the ecliptic. So because we're tilted at 23.5 degrees, we can actually do 90 minus our latitude and actually figure out, well, what this angle is. And then if we take the moon's orbit and I rotate this all the way around, keeping the most tangent heavy area, now we have a look at this blue line. So this blue line goes from the observer to the moon. And if we look at this blue line in relation to in fact, wait a minute, I have to swap something. Apologies, because I set this up so that I could do this. Where do I aim? Aim, and we are aiming at not the sun, we're aiming at the moon model. There we go. So that's we're actually looking at the moon there. It's there at the moment. This is a very wide angle camera, by the way. Now we can see now that the observer, which is in England, which is here, is looking at this angle away from the surface. So you can see it's not straight up, but it's probably only about 15 degrees shy of being straight up. And we can measure that here because I've got these, I built this radial widget, which is based on the normal direction of the surface, so the up vector. And each one of these dots relative to the camera view is 5 degrees. So I can say, well, that's 5, 10, 15, 20. So 23 degrees at the moment to the moon, or thereabouts. Off zenith, so off straight up. So that's how the moon would, in relation to our good selves, and this is the up vector of ourselves, that's straight up for ourselves, that's how the moon is actually along that blue line. And the difference between up and that blue line is pretty, you know, it's not a huge angle. Does that make sense?
Yes.
Hey, that was easy, then.
Yeah.
Again, most of this, like I say to most flat earthers, that I don't think flat earthers get what an amazing deal it would be to break the heliocentric model for a globe proponent. So, granted, I'd be taking some of the glory away from a flat earther, but if a flat earther pointed out to me something that didn't work by me simply rotating this sphere, in reality, that would be, pardon the pun, but astronomical. It would be awesome. And it would change so much, and I'd love it. But unfortunately, boring as it is, this thing kind of always works.
Overhead. I mean, I don't see really from like how you've positioned it on the screen how it's near enough directly overhead if it's only like 5 degrees above the equator. Can you show me above the equator?
So the equator, well, when you say above the equator, it depends what you mean, because the equator is this 23.5 degree offset. So if we look at this kind of angled box here, you can think of the equator as halfway up, this kind of red line here. So when it's 23.5 degrees above the equator, it depends where you're looking at it, because we're on a sphere. We're on a globe, which means wherever you are on the globe, you're looking at a different angle to the moon. You can, and most flat earthers can actually verify this. You're also looking at a different orientation because you're on a globe. Again, something that you can verify. So if I zoomed in here and then I moved the observer position, we can see that in Argentina it's upside down because our up vector is inverse to what it was when we were in the UK. So in Argentina, if you look at photos of the moon, it's actually upside down. It isn't really, obviously.
That's not because you're in a different hemisphere. That can happen on a flat Earth as well, that it can be a different orientation.
It can be a different orientation. It can never be upside down.
It can. If you put, like, for example, a number on the ceiling, and then you walk from one side of the room to the other, and then just basically bend your head backwards, it's basically upside down. It's not the fact. You're like a telescope in that scenario where you're bending backwards kind of thing. It's upside down, but it's not really upside down. It's just your perspective.
So the amazing thing about that is I don't need to do the numbers example. I can actually just try it on a flat Earth in every kind of conceivable way. Now the numbers example is fine if the moon was flat, and if the moon mutated its shape, because if you put a number, so imagine you put the number like 2, and then you put a circle around that number. There is only one place on that ceiling that would be a circle, and that will be directly underneath. If you move left, right, forwards, backwards, it becomes an oval shape. Now, the important thing about a flat Earth and the moon here is this is the only side of the moon that we see. And in Argentina, we kind of see that. No amount of movement on a flat plane can actually do that. And also, in Australia, they would see the ass end of the moon, something that we absolutely do not see. Sorry, you're breaking up.
I used to say to the Globers that basically, did the orientation of the moon being upside down in the southern hemisphere mean that it's a globe? And they was like, no, because they understood that actually you could look at it from a different direction or have a telescope which is bent backwards kind of thing and still see it upside down. It doesn't necessarily mean that you've changed your orientation as in you're in the bottom of the globe.
So the thing about upside down and all that kind of stuff is on a globe, obviously, where that's relative to the up vector, which is always the opposite of the center of a planet. Now,
yeah,
that on a flat surface is really easy because there's no divergence there. It doesn't matter where I am on this flat surface. Up is always up. This Z coordinate is always in the same direction, and it's always parallel to everywhere else. Now, the issue with that for flat Earth is that now I can move the observer. Have I got the moon on here? Wait a minute. I've got this little dude. Just bear with me. What camera is this? Camera observer A. Jesus Christ, I need better naming. Camera observer A1. So now we're looking at the moon. Now, there is no shape. There's no geometry. There's no flat or sphere. There's no way at all for me to replicate what I see in reality. No, I don't. I could get rid of this map. The map is irrelevant. I just move this around anywhere, and I cannot ever match reality. Now, don't get me wrong. There will be one occasion where I can, but that will only ever work for that one location at one moment in time. Once time moves forward or backwards, it doesn't work. And if I move the location, it doesn't work. Or if we have more than one observer, it doesn't work. So if you can, and I genuinely mean this, if you can tell me what to do with this model so that this observer on the right here can actually, I can place, I can see how we see the sun in the, how we see the moon in the UK. So let's do this and then just pull the moon round. So that's about where we'd see the moon in the UK. It actually doesn't match because it's more a case of it's like that. Now, bear in mind, I could actually say, hey, this could match at some point in the year. This could actually match reality now. The problem is it doesn't match reality when it moves off like that. That's when it doesn't start to match. And at the same moment in time, it doesn't match the African view or the Southern African view because it's just we've never seen this part of the moon. This is the backside of the moon, and we don't see that. So if you can tell me how I can have an observer where I'm here in the UK, I'm here in good old friendly Argentina, looking at an upside down version of the one in the UK, because those plainly, these vectors plainly don't match looking at a spherical object, and they absolutely wouldn't match looking at a circular one. Do you understand the issues here?
Yeah, but I have a couple of suggestions.
Yeah, go for it.
Okay, so the first one would be instead of having the moon orbit like literally above the Earth, have it orbit around the outside of it. Okay. So it's facing you constantly, but orbiting around the outside of the Earth. Does that make sense?
Yeah, that's fine. So we're on about more of a distance like out here.
Yeah, like outside the flat Earth and then orbiting around the outside, always keeping that one face to you.
Yeah. So
the second thing I would say is...
Sorry, go on.
Yeah, the second thing I would say is have the north one side and the south the other side. So it's almost like a figure of eight, like an infinity symbol.
What is, sorry? The path of
flat Earth. The flat Earth. So it's like an oval, but like an infinity symbol, if that makes sense. Like a figure of eight sideways. Yeah, so you have north one side and the south the other, where it's like bigger at the equator though, so it's not quite an infinity symbol, but almost similar, if that makes sense.
I think you'd have to draw this because this is a bit weird. Because the infinity symbol to me is obviously like a figure of eight, where it has a very narrow bit. Where would that very narrow bit be, or what would be on that narrow bit in reality? Like if I wanted to say...
Well, imagine the narrow bit of the infinity symbol, but imagine it wider than the edges. So it's like the infinity symbol, but the middle bit's wider actually than the outside.
Yeah, that's definitely a shape that you have to show me. But just going back to this really quickly, if we look at this now, and granted, this could work for one observer again. Can you now tell me how someone in Argentina sees that? Because I have to keep it this orientation and only move this observer on a flat plane and somehow get the bottom to be the top and the top be the bottom while it's still facing me. That's what I've got a problem with. Oh, sorry, you're breaking up, Rach. You there?
Problems.
I don't know, go close.
There you go. Yeah, now we got you.
Okay, so imagine, just try different numbers on the symbols. Now imagine on the ceiling. Now imagine one side is north, one side is south. And as you walk from one side to the other side, as you look backwards like a telescope would, you would see that it's actually upside down, even though it's really not upside down.
So So that would only happen. So let's do this as an example then. This is now on the ceiling, yeah? So if I take this observer, it doesn't matter where we are, if I walk underneath it and I'm looking up, I'm seeing a completely different side of it, and it's not actually upside down. It will never be upside down if my feet are on the floor and I look up at it. It will only ever be upside down if I bend backwards with my eyes and go all the way over. That's not what we do. What we do is just, at the moment where this is directly underneath, we wouldn't sort of like carry on walking and then fall over backwards. We'd turn around like this camera does, like that. Can you see it turn? So it's always looking down from zenith at the moon. So we don't go upside down and then backwards over and then stay looking backwards while falling on our backs. We turn around and look at it just like this camera does. Otherwise, we'd have a very big problem walking forwards.
But your camera's showing it being upside down.
So my camera here is actually showing the backside of the moon, really big issue. But my camera's not showing it upside down here. It's still actually the same way. The top is the top, the bottom is the bottom. So if I turn this round, and I'm not changing the up and down, I'm just turning it round. That's still at the top, the cluster of things like we see in the UK. You know, the cluster of big craters and shit. I'm not a moon expert, but whatever the hell they are. And all I'm doing is rotating it. I'm not turning it up or down. I'm just correcting for the fact that now we've walked around the back of it, something that we can't actually do. So this hasn't...
But have you got it tidally locked around the outside of it?
Sorry, say again.
Have you got it tidally locked around the outside of the flat Earth?
No, because I have to walk underneath it, you said. So I can't have it out there and then fly out there under the flat Earth.
It's perspective, isn't it? It's the same as the globe Earth. Like, they've got the sun, but the sun doesn't actually come in at that angle. There's refraction and things that take place, which puts it actually at a different position to what you see.
Yeah, no, absolutely. So there's two things with the sun. One is the temporal difference. So we're actually lagging 8 minutes behind. And like you say, the other is refraction. However, we can pretty much disregard refraction on average above 10 degrees. So anywhere above 10 degrees, write it off, because the fractional difference of the degrees is so infinitesimally small that for the sake of using observations and us measuring it with a protractor or an inclinometer or an accelerometer wouldn't actually make that much of a difference. So refraction, throw it away. Doesn't matter. It's not some magic.
Okay, do you agree that refraction happens when you go into a denser medium?
Yes.
Okay, so if you was to go from the vacuum of space into the atmosphere, which is a denser medium, would you agree there is a refraction?
Yes.
So therefore, you're going to get refraction even if it's straight up zenith, because you're going from a vacuum, or what's meant to be a vacuum, into a medium. So you're going to get refraction either way.
Do you know the three important elements of Snell's law for refraction?
I know you need a change in medium or a change in density, which changes the wave speed, which causes refraction.
Yeah. So you've got so first of all, you've got the base medium, which you would have an index of refraction for, and then you'd have a second medium, which you have an index of refraction for. You've then got an incidence angle and then a reflection angle, and the reflection angle is determined by the incidence angle in relation to the two medium changes. And the less of an angle that... So an example there is between nothing and air, there is an incredibly small amount of difference. And at acute angles, that's where it will be at its greatest. So if we disregard the 10 degrees at the horizon and just write that off, it's pretty much zero, or I'll even give you, it's 0.1 of a degree. And that's quite a lot. In just standard atmospheric refraction of the light coming in, hitting the atmosphere and going through. So I'll give you 0.1 degree, but let's make our error tolerance. I'll give you 0.1 degree, but let's make it 5 degrees error tolerance. So now we can just throw refraction out, hellishly. And we're left with, okay, so any observational prediction that we make now will plus minus 5 degrees to, it still doesn't work here. it's so far off, it doesn't work. It doesn't turn the moon upside down at all. It just can't. So refraction, the thing about flat Earth, and my one criticism about most flat Earth arguments is there's always these qualifying statements. I will have you accounted for refraction. What is good to hear after that is because refraction, given this, would do this at this magnitude. Because the issue is, above 10 degrees, the degree change of where something apparently is to where it physically is so infinitesimally small. We lost her.
Hello. Sorry, my battery died. Every time, man.
So just really quickly, Rachel, where we left off. If the moon is so far out there, how would we ever see it over the United Kingdom, pretty much very high up, 20 degrees off zenith?
That's a good question. I don't really know.
No.
All I know is that I think south one side, north the other, and I just didn't understand how it could get pretty much straight above us if it was like 5-6 degrees off the equator.
Yeah, but you kind of do now, and it's 5.12 degrees, and it's not the equator. That's the thing that confused me. It's off the ecliptic, so the solar plane, it's 5.14 degrees or something up from, or whatever I set it to. I did look up the number, and then the Earth is tilted 23.5. So those two accumulated, and our latitude in the UK can give us kind of a 20 degree from zenith kind of view of the moon. One of the other issues that I've got with a flat Earth, and I'm interested in your infinity thing. So it would be cool. I mean, you don't have to do it now, obviously, but if you could draw like an outline of it, because I could actually make, I could make it to see how things work. Because I'll give you an example of, I don't know whether you've ever seen this, but I'll give you an example of another observation. So let me have a look at this. Camera Observer A. So if I go to Camera Observer A, what we've got here on the right, if you're viewing my screen, is a view from Melbourne, Australia, of the sun. Now I can move this on the tropics so that it is the closest it's ever going to be to Australia, and we see it
and
come
it
past
doesn't set
Australia.
in the right place.
Well, it's not just that. I'll tell you a number of questions. I'll tell you a number of issues. So it doesn't matter what I do. The angle doesn't match. The motion doesn't match. The path through the sky doesn't match. The angular size change doesn't match, and the angular velocity doesn't match. It would accelerate immensely as it came past. Doesn't match. Now, just to show you, and it doesn't matter where I put these on the tropics, none of them match. Now, what someone in Melbourne, Australia, on a flat Earth, and I'm saying, hey, the Earth is flat here. What they would actually see is this. And that would work for someone in Australia is this, it coming over. Now, it wouldn't work for someone in Sydney, which is not that far from Melbourne. And it certainly wouldn't work for someone in New Zealand, the Philippines, but it would work for that single person in Sydney. Do you see the kind of motion that would have to go through here? That's what they see at this period in time. So no matter, and honestly, I have tried a number of ways to come up with weird and wonderful physics to make all of this work. I'll give you one other example of how there's an issue with it, and that's we transverse electromagnetic wave theory is pretty much understood. So everything about visible light and non-visible light, and we know that the inverse square law is a thing. And the issue that we have, and you can buy a very basic camera equipment and a light meter to figure this out, is the fractional, just like the angular size not changing being an issue, the actual energy readout from this light source, the light actually coming in, that electromagnetic wave, or those electromagnetic energy, we double the distance here. So from here on the tropics, and it moving here, we've doubled the distance. Do you know what that would do to the intensity of light, especially through our atmosphere?
If you double the distance.
That would quarter the energy, which we've got an issue with because that's not what we see. That means it would only ever be, let's say our day would be absolutely so bright when the sun is overhead. But the second it gets here, our day would be less than half as bright. And this here is only 1 hour later on a flat Earth. 2 hours later on. Sorry, go on.
But are you taking into effect the effects of the dome?
No one's ever told me the physical properties or physics properties of what the dome would do to light.
Well, it would be a kind of container. So how I imagine it is what they call the ionosphere. So they call this thing the ionosphere that can bounce radio waves off it and things. I don't think it's like made of glass or anything solid. I think it's something that can be penetrated, but it still keeps the gas and things in here. Like, do you know what I mean? Like, so that would have an effect on the sun if the sun's outside of that container, that dome.
Oh, so you're saying so the sun isn't, because this is 4,000 miles high, by the way. I think. Wait a minute. What is this? This is yeah, near enough. But it's not. It's a lot higher, is it? The sun.
But it'd be outside the dome, and then it'd obviously coming through the ionosphere, what you call the ionosphere, which would be like a protective layer which you bounce radio waves off. And that protective layer would obviously have an effect on the light coming in.
Yeah, when you say bounce radio waves, you are on about a very, very specific frequency, and you have to also account for a huge scatter coefficient in that. It's not like something that you can just aim any radio wave at and hey presto, there you go. 99.999% of radio waves go straight through that.
Right. The gas, if it was to go up there, would bounce back off it and come back down.
Sorry, say again.
So, like, if we had the ionosphere, the gas, for all we know, could go up there, bounce off this ionosphere, this dome, this ionosphere, and bounce back down.
The gas
and
or the light?
The gas and the light. So the gas would basically bounce off it and bounce back down, and the light, as it comes through, would hit this ionosphere or this dome, whatever you want to call it, and it would obviously, you know, come in at a different angle to what it's actually at.
Yes. So one of the issues that we have there is that dome, much like a lens. Well, so there's two aspects to that. We can move straight back to Snell's law for that. If you say the dome isn't physical, we have an issue. Snell's law only works with definitive boundary conditions. Now we have to go with Fermat's principle because we have graduation. Now, if this graduation is not homogeneous and linear in its predictability, that means now it's acting like a fluid or a liquid and is non-consistent, which now means much like looking through a caustic effect of water at a light source that you see is shimmering, we would see the same thing. The only thing that would negate that is it is homogeneous, there's a linear effect, and the depth of it is consistent throughout. That's the only thing. But that actually doesn't then move the position of the light coming through it. Because if you think it slows it down during, but it exits with the same tangent. Because if you think of a fighter pilot and he's got his cockpit there, that cockpit being the same thickness all the way through, even though that shape is domed, and sometimes not just domed, it goes from like a little bit flat to a little bit more domed to a little bit oval to like egg-shaped. But he can look at any direction and just see clear sky with very little to no distortion. And he needs to be able to do that, and that's because of the consistency of the thickness of the glass. So you can only have so there's only two possibilities here. One, it's the graduation on it is fuzzy, it's a non-linear effect, it's non-homogeneous, in which case the light through it would act accordingly to how we know, and it'd be like looking through water. Or it's a consistent thickness, much like the fighter pilot or the glass screen on your car, and doesn't distort at all. It just slows down the light and exits at the same reflection angle as the incident angle, which means it doesn't actually change the position of it. Now, if it's not got consistent depth, then it is operating more like a lens. Now, the issue with that is you do not get on a curving lens, especially a huge rounded thing like this, or how it would have to act. You do not get consistent distortion. And by that I mean, much like on a lens on a camera or glasses or things like that, if it's not a consistent thickness, it would not be a sphere coming through or a circle, an apparent circle. It would start mutating, and it would look very different based on your observer position. So out of all the three possibilities there, I can, in a physics sense, come up with one that would work, and I have the only way that I did it, and this was a stretch. The only way that I did it was I had a toroidal field, and which actually invented. So there was two things that I had to contend with. The inverse square law didn't work. I had to come up with something new. And I also had to come up with how the light would bend, even though the sun is in this position. How could I make a sunrise, a sunset, an apparent position? And I created a toroidal field that allowed me to bend the light rays, an undiscovered, physics property of light, to allow me to have sunset and sunrise. And it would act, I could actually come up with the vectors to make it semi-act. I mean, it wouldn't be 100% consistent, but I'd be able to get away with it a little bit. But then you're faced with an undeniable fact. And I think Farmer's Boy pointed this out to me. What happens when we have 24-hour sun in the southern pole? And that's just not a thing that can happen, which is why I'm interested in your figure of 8 thing, if it can happen on that. Or your infinity flat Earth.
Yeah, a flat Earth has said there is a toroidal field, and if there is a toroidal field, then maybe it could work, and then you could use the south one side and the north the other side, and then maybe it could work that way.
Yes, the interesting the problem that I had with the toroidal field is I could get sunrise and sunset. So apparently, to the observer in Australia, even though the sun was actually here, the toroidal field would make it look as though it was there. Yeah, absolutely would. I could do that. Brilliant, awesome. I'm still left with two other issues in terms of light from the sun. One again is the inverse square law. There is no evidence to support the assertion that that is not a constant in the TEM field. Yeah, none. So I have to try and figure out, well, now I need to come up with a new law, and I just invented one that actually worked. I had a different fall-off equation, but that's inventing something that's never been proved, you know, and not a thing. And then the other thing that I've got an issue with, terminator line. So now I've got the issue that, yes, I can get this sun down here, but what I also need to do is create a terminator line on the flat Earth somehow, which then actually pissed up my toroidal field, because now it's not a toroidal field. It's a toroidal field hitting a brick wall, an invisible brick wall, which creates a terminator line.
Okay, but would you agree that light can only travel so far?
No, I would not. I would say light, infinite is not a number. But if I said to you, you know, walk towards your door, and every minute I want you to take, I want you to halve the distance. Would you ever make it to the door? No. Now,
okay, but if I use your model, yeah, your model says.
Sorry. Let me answer that in another way. I just want to clarify. Light is not infinite. Light in a vacuum is for all intents and purposes infinite as long as you can read the minutiae of it. But no, light isn't infinite if we're talking about in a pragmatic sense, as in can we see it, can we read it, kind of thing.
I was going to say, because like in your model, the universe is meant to be flat, but you can't actually see every single light source, like star, for example, that's out there. Like you can only see the observable universe, as they call it. You can't see what's beyond the observable universe, even though the universe is flat, or they say it's flat. So you can't really see forever, even in your model, right?
So again, that's a qualifying statement, and we have to dig into the details of why. So I could fire up one of my cameras right now, and in a pitch black room, or seemingly pitch black room, take a very bright photo for you without using a flash. How could I do that with very little or no light that I can't see with the human eye? Well, what I can do is I can leave the exposure on the camera open for, well, I've actually got something called bulb mode. That will allow me to leave it open for as long as I want. Which means it would just take one, if I wanted to, that time could be infinite. And if one or two photons made it into the room, I'd get a picture because they just bounce around and illuminate everything. So it depends on your sensor device. So can we see distant stars with the naked eye through the atmosphere? No. Can we see more if we go up outside of the atmosphere and look through a window on the ISS? Yes. What about if we point a camera into the Gulf of Space and just take an RGB photo? Yes. But there's still black spots. What about if we point at the black spots and use infrared? Can we now see more? Yes. What about if we boost the gain ISO and expose that for 50 minutes? Can we see more? Yes. So it's not a clear-cut answer. We can always see more. Cameras can always see more with better technology.
Okay, so on a flat Earth, would you agree if we lived on a flat Earth, things would appear lower with distance?
Only to the laws of perspective, yes.
So when they reach that lowest distance according to the laws of perspective, then what would happen in your opinion? Do you think you'd still be able to see that thing as it gets further and further and further and further and further away?
So this is a calculation you can do, and you can actually do it without a perspective algorithm. You can do it with basic trigonometry. So let's take this for example, this sun. So if I can assume any height, but let's start at a number, and let's say 4,000 miles. This sun is 4,000 miles high. Now, this sun needs to go far enough away so that an observer on the ground can see it close to the surface of the Earth. Sorry, say
So
that
the
again.
problem with this doing trigonometry is all you're doing is drawing straight lines, basically doing angles, doing triangles. You're not actually taking into consideration the atmosphere or any other effects. All you're doing is literally straight lines on paper kind of thing. You're not taking into consideration any actual effects of the reality.
Okay. So that's a qualifying statement. Quantify it for me. What should I take into consideration, and what would be the magnitude of the effect?
That I do not know. All I know is that, we get refraction, as you call it, but I believe it works the opposite way. And
okay. Let's stop on that 2 seconds. So you're saying that Snell's law operates inversely to what is defined there?
Yeah, the opposite way. Yeah.
Right. So So you do realise that if that were the case, the glasses that I am wearing right now, along with every single camera lens, would not work.
Why?
Because that takes into consideration Snell's law with convex and concave surfaces and different density changes that only work on boundary conditions, incidence and reflection angles. And it is computer controlled to the sub-micron level, built off Snell's law, as are my glasses.
In simple terms, if you don't mind.
Sorry, say that again, Rachel.
Can you say that in simple terms?
Right, so if Snell's law is not a thing, then every single reliance on that law we have to reevaluate because it would be wrong. Now, if it is inverse, that would mean that a concave lens element that collimates light in a lens, or the glasses on my face right now, would actually do the opposite to what they actually do. It would be demonstrable and testable.
But why do you say that? Why do you say it would do the opposite of what they do?
Okay, so wait a minute. Let me show you this.
Because I've done experiments with refraction, and to me, it always seems like it's coming out the dense medium into the less dense medium, which then actually causes the object to, change position.
I had to jump in because StingRay say doo-doo. What an infantile comment. Shout out to everybody in YouTube land. Please hit the like if you haven't done so. Share the show and carry on, guys. I had to.
Yeah, wait a minute. I'm just trying to find. Wait a minute. Density, sun, dome. My God, I do too many 3D graphics files. Where are we? Perspective examples. Volume scatter, space, shadow, penumbra, refraction. This might be it. Okay, so if you can still see my screen, yes?
Yeah.
Rachie? Hello. All right, I think you're saying yes, but it's cutting out.
Yeah.
So a very important thing about this, which is in fact a lens element, because not only is it understood in real life and do we use it, it's actually understood in computer graphics as well, and we absolutely use it. So what I'm going to do now is I'm going to render, which is a brute force ray tracer, which traces rays through this medium, which is a glass element, to this block here. Now, can you see what's happening to this block? This block I've highlighted in the bottom is in a physical location, but now is in a apparent location through the lens. So I'm moving it, it kind of matches up, but it's magnifying. It's magnifying it because, quite rightly, this is a convex lens element where it's thicker in the middle, and when the light comes in using Snell's law, it spreads out further, which gives us, based on the distance, a narrower view of that light, which causes magnification. Now, this is all built on Snell's law, as is demonstrable in a magnifying glass. Now, if this wasn't the case, a magnifying glass would make things get smaller, not bigger, if it worked inversely. you can trace, using Snell's law, incidence, reflection, and index of refraction. So in air, I think it's 1.03. Glass, or certain grades of glass will say 1.33, which is fractional reduction in light speed. Incidence angle, you can work it out to figure out what we're going to see in this lens. And if it wasn't true, it would be so apparent in absolutely everything, from a magnifying glass to my glasses to all my camera lenses. And that's, and like I say, I as much as it's an interesting theory, I mean, just to support you a little bit here, I did actually, I mean, Snell's law, there's a reason it's called a law. That doesn't mean that you could be entirely wrong. So if here I've got bands of atmosphere with only 3 boundary conditions, just to simulate what the atmosphere would do. So in standard atmospheric refraction, in an absolutely heavy refraction day, it will make a curved surface like this look flat, like it does do through the medium change. Now, if we move further along, we have, well, what would happen on a flat Earth with standard refraction? Well, it would actually make it look as though it's rising upward, but with actually concave Earth. Now, here's what I think you're getting at, and that's, well, what would happen if light in the atmosphere bent upwards instead of downwards? So let's forget about Snell's law, because that's a law. But what about in the atmosphere if light bent up rather than down? What we'd get
That's not what I'm saying.
All right, because that would work.
What I'm saying is the light still bends down, but how you say it raises the image up, then it doesn't, then it raises the image down. So when light bends down, the image goes down. When light bends up, the image is up.
No, that's the opposite.
See, because Snell's law is generally only true for the isotropic or the specular media. It's not true for every single medium.
So the medium, or, well, the only thing that's important is the index of refraction. If you were to get down to physics, you'd also want the absorption and scatter coefficients as well. But if we just stick with what path does light take, the only 3 elements are the index of refraction differential, the incident angle, and then we get the reflecting angle. Now,
what about the extraordinary or the E-ray?
Wait a minute. If we go back to your statement of bending light down causes things to appear lower.
Yeah.
That I've heard that a few times with flat earthers, and that's the opposite. So this example here. Oh, in fact, let's go to the flat one. So this is flat Earth. These blocks are all flat here. And the light is being bent downwards. Now that causes an apparent, that causes an apparent heightening in objects of where they are. So this red thing is actually that red thing in the background. It just appears higher because the light has been bent down. Because the only thing that's important with light bending down, or with light in general, is the incidence angle at your eye. So if something comes in pointing downwards, apparently it's high up in your vision. If something comes in pointing upwards, apparently it's low down in your vision. So now we can assume that if light left in straight lines, but then bent downwards, that because it's coming downwards into your eye, we trace straight apparent lines from your eye from that incidence angle, and we get something that appears higher. And that's how light bending down causes things to appear higher, like we're seeing here with this example.
Okay.
Sorry, say again. I think you need to sit closer to your router, I think.
Yeah, you broke up there for the second time. A little bit of robotic.
That. Any evidence?
Oh, sorry. Say that again, Rachie.
Any evidence? We heard that part.
Yeah.
Fucking internet, them fake satellites. Don't letting Rachie get a good signal.
Fake satellites. Yeah. Well, Wi-Fi. Hmm.
Yeah. They're on to me.
There you go. I'll hear you now.
Okay.
No, you jinxed it, Jose. Not hearing a word of that, Rachel. Really sorry.
No.
I think you can actually sit too close to your Wi-Fi, you know.
What we can hear is like a little bit of a like an attempt to talk, but no words are coming through. Like not a complete sentence at all. Very, very broken up. No, still. Yep. Drop and rejoin. That might fix it. She just dropped. Hopefully when she... Alright, let's see if that will sort it out. No.
No.
Oh.
That last no was solid. I know. It comes and goes whenever the fuck the signal wants. Set up a gun. When you're talking, look at your phone.
No, man.
There you go. Yeah, there you go. Look at your phone. It should have some like little green lines, like the voice connected. If it got at least 2 lines, I think there are like 3 lines. It says voice connected. If you got at least two lines, we should hear you okay.
No. Ah, man.
Every time you say no and man, it comes out really clearly.
Yeah.
You know when you start with a sentence, it dies.
It's not.
This sucks. That's unfortunate. Damn it.
Just so you know, microwaves operate at a very similar frequency to your low band Wi-Fi at 2.4 gigahertz. So, if someone's cooking something in the microwave and there's a lot of bleed, then that might screw you. Yeah.
Nobody's cooking nothing in the microwave.
Well, I heard that nobody's cooking nothing in the microwave. Yeah, we'll keep attending.
Yeah. No. Yeah.
yeah, no, yeah. Yeah. This is going good, but it's just, I mean, it's just the signal is betraying you. Oh man, that's messed up. Well, let me while hopefully we get Rachie back on. The link for Rachie.
How about now?
Oh yeah,
Oh, wow.
beautiful. Hell yeah, I go on mute. Go ahead.
I turned my headphones off.
Oh, your headphones.
Yeah, now I've turned them off.
Oh yeah, no, that's as if you stood in the next room to me. That's weird. I think you need
It's
some
strange.
new
I
headphones.
thought that would have been better.
No, I think you need some new headphones. Jesus. So just really quickly on that last point, Rachel. On a curve here, which is the left-hand side, and what happens to boats? Because you were asking about things disappearing, in the distance, kind of thing. And the only thing that I can do in a 3D program is use perspective. That's it. And the perspective equations just mean that if we double the distance, we halve the size. It's literally that simple. But I decided on the left-hand side here, which is the curved 345 miles, 5-degree curvature. By the way, these vessels only exist in the first like 8 miles, so you can see them
StingRay.
here. Yeah.
I recommend you, because Rachie is on a phone, to maybe maximize, like now she see the setup like in the bottom, kind of the overall, but whenever you're going to do the little presentation, just maximize that so she can see it a little better. It's a smaller screen. Is that fair, Rachie?
Now she might have a
Yeah,
massive.
yeah.
Oh.
Good.
But yeah, so Rachie, this so even though both of these look flat at only 8 miles, we see the effect of curvature. Now, what I decided to do at this side is to be able to simulate refraction and the effect that it would give in the bending of light. So if I take all of this and I bend light predominantly downwards, so a curve and bending light downwards, I can actually make it seem flat because the light is coming in at a higher angle, but only very slightly. Now, the distances that match up geometrically are this. What we probably see in reality is more like that. Now, here's the interesting thing. On a flat Earth, this would be it geometrically. But given an atmosphere and light bending down like we know that it does, we'd probably see something like that. That's with light bending downwards. And you can see out here that there is a ship. This is 300 miles away. Well, you probably can't see it actually, but it's 300 miles away in the distance. But you would be able to see it on a flat Earth, especially since light bends downwards through the atmosphere.
Is that using Snell's law?
No, this would be, because it's graduation, this would be Fermat's principle. Because it's Snell's law, like I say, works on boundary conditions. And through the atmosphere, you've got a stupid amount, you've got an infinitesimal amount of boundary conditions, a limitless amount. So you can, but we use Snell's law for, like, obviously, lenses, my glasses, your glasses if you wear them.
Yeah, because Snell's law is generally only true for isotropic and specular media, right?
It's true for any. It depends what light frequency or what electromagnetic frequency you're on about, and if it's penetrable, it's just about density change.
Well, if it's anisotropic, I can't even say the word. Anisotropic, yeah. Then wouldn't it be different then?
What do you mean? Would it be different than what?
Wouldn't it change the way that Snell's law works?
No. If it's, like I say, if it's got a boundary condition, so a definitive change, so like glass and air, or air and water, then you can calculate that just through the density change. And like I say, the only other two things, the only things that you need is the density difference in the index of refraction and the incidence angle to come up with the reflecting angle. And that's it.
But would you agree the I can't even say the word. But yeah, that thing, yeah. Would you agree that reflects it into 2 rays?
Reflects what into 2 rays?
It refracts the light that you're looking at into 2 different rays.
So in material properties, you can have divergence, but that's not a photon splitting into 2, because you can have a scatter coefficient of a material. There are actually there are university spectral imaging scanners where you can go and do this. I did this once probably about 8 years, well, no, more than 8 years ago, 15 years ago, and it allowed what it does is it shoves a high intensity laser through objects to get physical properties in order to simulate it better. So so you could shove a bar of soap in there, and it would give you the scatter coefficients and absorption coefficients within the materials. Now, can you get light divergence through a non-homogeneous medium? Absolutely, you can. And you can. There's a telltale sign of that. Do you know what the telltale sign of it is? Things cease to look how you expect them to look. So to give you an example,
So would you say that could be the dome?
No. Well, let me finish with this example first. So
Okay.
first of all, let's define it. What does a non-homogeneous, light divergent, kind of scattery thing mean? Well, it means that now a box wouldn't look like a box. It would look like we're looking through a slight liquid, and it would potentially change because if it involves fluid dynamics, it's not going to be a constant. It's going to be changing at some rate. So now a box isn't a box. It's more like a square that's got wavy lines on it. Or another example would be the very, very rigid arm of an oil rig bending and being not like reality. We can then say,
so just like the black swan.
A little bit like that, yeah, or anything. A mirage.
So reality, because we've seen the black swan in reality, right?
Sorry?
So like reality, because the black swan was reality, right?
Black swan is reality, yes.
So if we've seen it bending and it can do that to things, and we see that effect, then it could be that effect, right?
What could be that effect?
Well, you said that it could cause like the bending of the oil rigs, for example. We've seen bending of the oil rig, so it could cause that effect. So it could be that that's actually the cause, because that's the effect that we would expect from the cause.
But the cause of what? You mean how the sun?
The cause of how it bends, like how you said the oil rigs would bend. Yeah. Because of that cause, we see that effect, and we photographed and videoed that effect. So how do we know that that's not the cause of that effect?
So I don't quite follow you. The cause. So the cause of that effect is the divergence of light through the atmosphere. So when you have heavy refraction, because the atmosphere is the atmosphere is a fluid, it conforms to fluid dynamics. Yeah. Now what that means is no single photon is going to follow the same path. If they leave parallel, there'll be slight divergence, and that divergence is due to the fluid nature of the atmosphere and refraction and how it affects it. And we can tell that because, like I say, things become wavy. It's like we're looking through a fluid. Now, the important point there is, how does that relate to flat Earth? Well, if you think about those oil rigs, and you take, we can just say, well, what's the apparent position of that boom? And then we can take the where the pixel should be if the boom was straight, where it actually is. And if we measure the angular difference of that, we come up with it's probably moved 0.2 of a degree. So can that be responsible for any rational explanation of flat Earth, sunrise, sunset, moon? No, because the error I could give you 5 degrees. No. I could give you
but it's
10
over
degrees.
A larger distance as well, the moon and the sun, right?
Yes.
So therefore that could affect it more than just the oil rigs at like 10 miles, 15 miles, wherever they are.
It could indeed, yes.
So it could actually make the sun rise and set depending on the distance and how much effect that has on it.
No, because refraction, refraction and bending towards the denser medium cannot cause something to get lower. It can cause something to get higher, predominantly. So refraction.
Okay, so FTFE showed one video, and it was showing a blue thing and a red thing above a tank, and they put some butane liquid on it. Now, from when it entered the light, like come off the object through the butane, which would be more dense, into the air, which would be less dense, and hit the camera. Therefore, it's going from more dense to less dense, which made that basically rise. So therefore, if it was going to less dense to more dense, it would make it lower.
Yeah. So the issue there is you're looking at the wrong axis. So you're looking at a depth-based axis, which is not how the atmosphere works, and not how we account for refraction or atmospheric refraction, or even the refraction in the butane example. Now,
so why did they use that example?
Sorry?
Why did they use that example then if it's not,
because
analogous?
Yeah. So what that does is it creates a dense curve of air on the surface, and then it's less about a boundary condition like depth wise in Z moving away from you. It's more about it entering a medium whereby it's dense. So if we think of the light ray leaving that red thing or whatever it was, green thing, whatever you said, and it's going to try and make it to our eye, but it doesn't because the barrel's in the way, and then that light ray goes over our head and we never see it, never gets to our eye. Now, if we can make the atmosphere very dense around the surface by supercooling it, what that ray then does, or that photon is, and if we get down to it, it is actually, it's been affected by the fields of electrons in the denser medium that are below it, and it's been pulled towards those, which means now it starts to bend down, which now means it does make it round, that barrel, and enters our eye, which makes it appear higher. So it's not.
See, but that's the thing. It didn't do that. What it did was it went up into the denser medium because it was behind the barrel. So it went up into the denser medium that he poured, and then it went down from that denser medium that he poured to the camera, which was below that butane tank, below that tank that they was using as the horizon, and then it went down from there into the camera. So that doesn't work with what you say about refraction.
Well, it kind of does. Let me show you. I'll show you my screen again. I'll just do it in a 2D view. So if we've got an observer here, and this is actually the field of view of the observer, like so. And I've got something like a cylinder here. We'll have it flat on, because I'm guessing this is the example about what they did anyway.
Yeah, essentially.
Yeah, so it's probably they probably used a bigger cylinder, actually, a bigger surface. Oh, not that big. And then we've got another. Well, we'll actually have another cylinder because can't be asked. So we've got another cylinder behind it. Now, up and down are not really a thing that we should be concerned with here. All we're concerned with is this is the source, this is the observer, and a light ray.
No, the observer was lower than that.
Wait, it wouldn't matter. We can make it anywhere we want, really.
No, but it matters with the experiment and the observation that took place, because obviously we're going to tell what happened during that observation. So we need to make sure that the observer is where the observer is, and that wasn't higher, it was lower. Yeah,
that's fine. Okay, so we have an observer. The only thing that's actually important is this angle.
No, what's important is where the refraction happens. So, like, if the observer is lower, then he's lower. If the observer's higher, then he's higher. If the refracted ray comes higher, then the observer's higher, then obviously it's going to come to him. If he's lower, then obviously the refracted angle needs to go lower to go to him. So he needs to be lower because the camera was lower than the tank.
Right, I'll tell you what, let's use this as an example then. So this now is looking this way, and this is what the observer sees.
Yep.
Because I'm just trying to do an extreme example here, and then this is an object. Now, so observer here. Now, if a light ray leaves this, we can say that, well, hang about, there's no way that it's ever going to make it, to the observer.
Yeah.
Yeah. So what we have to do then is, if we increase the density here. So let's say here, this is incredibly dense in this fashion. So more dense, lower down. And the way that we do that is we cool this surface, supercool it. Yep. Now what that means is this ray that leaves here hits this dense layer. And now it doesn't matter whether this is up, down, upside down, doesn't matter. We're just on about a fixed coordinate where we've got transition of a ray. And all we know now is this is denser, which means it's going to start moving towards the denser medium and bend around, which now means it does get to the observer.
Okay, so what happens when it enters from a denser medium to a less dense medium?
So what you
Because
say?
you need to add that in because it's coming from that dense medium to the less dense medium to hit the camera. So you need to add that effect in when it's going from a dense medium to a less dense medium. You need to add that effect in.
Right. So there's no boundary condition here. All you need to all that's it's not. So the effect is this way. Yeah. The effect is that way. And the magnitude of the effect is that way. The ray is going this way. It doesn't actually matter that it's going to gradually hit something here. It doesn't, because the incidence angle of this isn't, it might make a difference and it might create that fluidy effect stuff. But the point is,
it makes a difference because when it goes in medium, it's meant to bounce down, and when it goes into a less dense medium, it's meant to bounce up. Now, what you're doing is it's going from a less dense medium into a more dense medium into a less dense medium, and then hitting the camera. You need to take those effects into consideration.
Yeah. So, okay. So let's say it does have an incidence angle and we are going to pay attention to it. And it's not a graduated thing. So right now it's hitting perpendicular, which means it does pretty much nothing. And then it's in here, but it's in this medium that's denser lower down and less dense higher up, which is the temperature differential of the supercooledness, which means it's going to bend down.
How would you say that's perpendicular?
Sorry, say again.
How would you determine that's perpendicular? Perpendicular to what?
Well, I'm just saying it's entering this what I've put on.
Yeah, but you said perpendicular. Perpendicular to what?
The density gradient.
How's that perpendicular?
It comes in at 90 degrees.
That's not 90 degrees.
This is near enough 90 degrees.
That is not 90 degrees. 90 degrees is a straight up line with a horizontal line. How is that 90 degrees?
Because if I take this and I take that, then this is 90 degrees.
Okay, I got you. Yeah.
But I mean, even if we get rid of this, let's say what it is. I drew this for simplicity, but in all seriousness, this isn't simple because what happened was more like this. Yeah, this is what happened, or this is what will have happened anyway. Now, what this means is rays that or light that leaves here is going to enter this and do all sorts of scattery shit, but predominantly bend to the denser medium and come out and wrap round, which allows the observer to see.
Going from a denser medium to a less dense medium.
So less dense, and then it enters here. This is forget about the more dense, less dense in this boundary condition. There's no boundary condition.
The more dense, less dense matters because that's what causes the refraction, because it causes a change of waves.
Right. So if we were to look at this here, everything inside this mess here is dense, and then inside this denseness is more denseness further down. So it's a graduated effect whereby at the surface, incredibly dense, and then it starts getting less dense to standard air density.
But would you agree when the light comes out of that density that it enters at a less dense then?
It comes out in a graduated fashion, yes. So if you imagine an incident, so if I drew this, let's say we did this like that. Let's assume that this is the same thickness. If light comes down here, it does that and then leaves there. That's what that does. Yeah? So
but
here
if light enters
a
a less dense medium, does it bend up or bend down, or does it go normal? What happens when it enters a less dense medium?
When it enters a less dense medium, it depends on the reflecting angle and the normal. So, like I say, this here, let's say this is 0 degrees. Yeah, it enters this at 0 degrees. This is dense. This is glass. It comes down here and it reflects. This is what we figure out from the difference in IOR, or index of refraction, for the air and the surface. But the normal here, it leaves at the same, if this is the same thickness all the way around, so that there's no actual density difference left or right, it leaves at that same 0 degrees. It is actually a little bit offset.
Okay, so I've noticed you've done it vertical there. So if we turn that 90 degrees so it was horizontal, like the actual light appeared in that experiment that FTFE showed, then obviously you would see that the horizontal line would come in, bend upwards, and then bend out, and it would be upwards. It wouldn't be nowhere near the observer, the camera, which is below the tank.
Yeah, so what you're
Which
concentrating
is why you drew it vertical to begin with, let's be honest, because you didn't want to show it horizontal the way that it would come out, because it wouldn't come out towards the observer. Would it?
Not quite.
No,
So
it wouldn't, would it?
So
So
what
you
you're
know
on
that
about?
refraction doesn't happen the way that you claim it to happen, do you?
I don't claim it. That's Snell's law. I'm not bright enough to.
Well, the way that Snell's law or the Globers or whatever you want to call it, the way that they claim it to happen, because the way that you just showed it there, vertical, you showed it coming down, going at an angle, then coming down again. Now, if we turn that 90 degrees sideways, you know that it wouldn't hit that observer, which is be below the tank, don't you?
Yeah. So
it wouldn't. So how does that happen then? Unless Snell's law is wrong.
So what you're getting confused at? So there's two things that happen here. We've got portion A, we've got event B, we've got C, we'll call this, and then we've got event D and then E. So the fact of this hitting a medium, that's dense, means that it's going to bend down. But this isn't a clear-cut line. There is no boundary condition here. So it's not a Snell's law boundary condition. It's a graduated thing. Now, when light hits this volume, it's a non-homogeneous volume.
Can you define boundary condition for me, just so I know that we're talking about the same thing?
So it's where we can definitively say one thing changes to another.
Okay,
so here we've got A and B, and everything
changes into a dense medium or a different medium.
So this is the boundary condition. The issue is, with this example, there is not the boundary condition here. There isn't one. Yeah?
Well, of course there is, because if you're going from the atmosphere and then you're going into liquid butane or whatever butane it was, then obviously you're going to have a boundary. Would you agree or disagree?
Disagree. So
why would you disagree?
Because on one side you've got butane, on the other side you've got air. Now there is a graduation between the two. There is not.
So would you agree that's going from one medium to another?
We could say this is B10. Here we can say this is B3. Here we can say this is B1. Here we can say this is A1, and then this is A10. So
is it going from a one density to a different density? Yes or no?
In a graduated form. So an infinite.
It doesn't matter graduated or not. Is it changing the wave speed when it enters the different medium, the butane? Is it changing the wave speed?
Yes.
Then there is refraction.
Yes.
Then therefore we have to make that refraction, we have to take that into account. And when it comes out of that medium, would you agree if it goes from a more dense medium to a less dense medium, there is another refraction?
So refraction is just the bending of light.
And would you agree if it goes from a dense medium to a less dense medium, there's still refraction?
There's refraction everywhere if there's a medium.
Yeah, so if it goes from a more dense, the butane, to a less dense, the air, would you agree that there's refraction?
In all honesty, you do not need boundary conditions, nor do you need two different types of...
No, all you need is a change of wave speed. So, okay, would you agree that the change of wave speed changes from the butane to the air?
Yes.
Okay, so when the wave speed goes from the butane to the air to the camera, which is obviously in the air, not in the butane, would you agree that it goes from more dense to less dense and that there is a change of wave speed and therefore a change of refraction?
Yes.
Yes. So if it goes from a more dense to a less dense, what is that change of refraction? So you say more dense makes things appear higher. So if it's going from more dense, which is a butane, to the less dense, and we've seen something get higher, and actually we know it went from the butane, which is more dense, to the less dense, and we saw it that the red thing got higher because we seen it cover the blue. Therefore, we know that obviously Snell's law works the opposite to what they say, because it comes from the butane, which was more dense, to the less dense, where the camera was. So obviously, when it goes from more dense to less dense, obviously that's what higher things up.
No. So
Well, that's what the experiment shows.
So I suggest you read Fermat's Principle.
See, that's the thing, ain't it? People suggest you read. Reading doesn't prove anything. Experiments do.
It doesn't, but it helps you understand graduated perturbation of light refraction.
No, reading doesn't help you understand anything. Experiments help you understand.
So it allows you to learn about non-boundary condition-based refraction. Now,
no, because reading doesn't teach you anything.
Okay.
I can read about unicorns. It doesn't teach me about unicorns. See, the thing is, what you need is experimentation. Now, we have seen experimentation with butane in the tank. We have seen it go from a more dense medium, which is the butane, to a less dense medium where the camera is. And we saw the effect. The effect was the thing rose. The red thing rose and covered the blue thing. And that's basically what it is. So it goes from more dense, which is the butane, to the less dense where the camera is, and it made something rise. So we already know Snell's law is wrong. Would you agree or disagree?
Disagree, because you're applying Snell's law to boundary conditions and then saying because something is butane and something is air, there's a boundary. The issue with
applying Snell's law to a change of wave speed. You agreed there was a change of wave speed if it went from a more dense butane to a less dense air. Agree or disagree? If there's a change of wave speed, there's refraction. Agree?
Yes.
Yes. So the change of wave speed, would you agree there's a change of wave speed from butane to air?
Yes.
Yes. So therefore, there's refraction from butane to air. Now, we had a camera in air. We had the object that we was observing in butane. It went from the butane to the air, which is more dense to less dense. There was a change of wave speed, therefore there was a refraction. It appeared higher to the camera. And to the camera, the light had to come from the object through the butane, which was more dense, to the less dense medium, which was the air, which was the camera was in. And therefore, we seen it rise higher. So therefore, going from more dense to less dense makes things appear higher, not the opposite way around, like you say.
Not like I say, like modern optics.
Well, like mainstream says.
Yeah. People who make glasses, optics, every kind of optic available say that. So the thing here, Rachie, is if I've got an object, and I'm going to draw this now so that we have got boundary condition. Yeah, this is now my boundary condition. This is butane, incredibly dense. Yeah, incredibly dense. Now, this isn't how it is, but I'm doing it because you want to invoke Snell's law and boundary conditions. So
no, I'm just saying, like, obviously there's a change of wave speed. He put the butane on, and there's a change of wave speed from the butane to the air, and you agree with that. So I'm not invoking straight in the Snell's law. No, it is what it is.
That's fine.
Change of wave speed, and that's what it is.
So it comes in and hits this surface. Yeah?
Yeah.
Now, it's more dense here and less dense up here. Incredibly so. Which means now...
It's even more or less dense where the camera is, right?
Yeah, no, let me finish. So...
Yeah, I'm just saying.
Yeah. So we got hit this at 90. Now, inside here, it's incredibly dense near this surface. And up here, it's almost air. So it's a graduated thing. So this light ray now bends round. It bends round. It bends round. And it leaves here. And we'll just for the sake of argument, at 90 degrees.
No. See, that's the thing. The way you drew that is not right. Because when it leaves there, it should not leave in a straight line.
This now appears in this location.
No. So look, you're saying that light bends down from a more dense to a less dense medium?
No.
That's what you draw right there. You drew right there from a more dense to a less dense, and you drew it bending down. Have you or have you not?
Right. So here is incredibly dense.
Yeah. Have you or have you not drew that bending down in a less dense medium?
Look at this. Let me finish. Nearly there. So this here is incredibly dense.
I'm just asking you a question.
Oh yeah, no, I'm answering you. This here, forget these boundary conditions for 2 seconds. I drew these in for you because you seem fascinated by them.
No, all I'm interested in is a change of wave speed, and a change of wave speed is refraction.
Here we go. So we can't think of this as just a consistent change of wave speed. We've got something that's less dense at the top of this and incredibly dense.
It doesn't matter about the top, though, does it?
So wait a minute. Yes, it actually does.
Why does it matter about the top? If light bends down to a more dense medium, why does it matter about the less dense at the top?
Because the electromagnetic fucking field force of things above it is less than below, which is why it bends in the first place. Let me finish this.
But you says that it bends down in a more dense medium. If it's less dense above and it's bending down in a more dense medium, then the less dense has F all to do with it, does it?
If up here produces an electromagnetic force of 1, and down here produces an attracting electromagnetic force of 10.
Okay, so
then
now
yes,
you're
it
bringing electromagnetic force in, right?
That's how light bends, yes.
Okay, so where was the electromagnetic force in all the other observations with the curve calculators and everything?
It's the density based on the field strength of the electrons.
It's the density, so it doesn't matter about less dense at the top. So it doesn't matter about the electromagnetic fields, and it matters about the density, and the density is more dense at the bottom. So you're bringing up electromagnet at the top, which is less dense, which is irrelevant because it bends down to the density, which you're saying anyway.
So if I've got a pulling force of 1 up here, but I've got a pulling force of 10 down here, I can pretty much say what's acting on this ray is 9 and it's going down. That's why it's important. So the butane...
Exactly, so there's no point even bringing the top into it then, is there?
So the butane, this is graduated. Dense at the top, less dense at the bottom, which means it's going to bend according to that. So yes,
what do you mean less dense at the bottom?
Relevant. It's the reason...
No, more dense at the bottom, not less dense.
Yes, incredibly dense down here, not dense at the top.
Yeah, you just said less dense.
All right, sorry. If I did say I said it wrong. So less dense at the bottom. Incredibly dense at the bottom, less dense at the top, which means during its transition, it's bending down, which means now when it leaves, it apparently looks higher up in relation to the eye, which is why you see it from behind. This is not something that is new. It's not something that is undiscovered, and it is actually described by well, Snell's law, if you draw it like this, kind of.
But you drew bent lines. Snell's law is not bent lines.
Then Fermat's principle, then.
Yeah, I'm going to have to look more into that one. I don't know that one.
Well, an easy way to think about it is just think of each one of these as you've got an infinite amount of boundary conditions. Yeah? Just an infinite amount. That's how we'd do it. And the other thing as well is this is, like I say, this is non-homogeneous, which means this ray bounces a little bit, which means the result is much like, let's have a look at this.
But there's one thing that you still missed on your example.
I got a quick comment to make in between, and I apologize, I shouldn't. Yeah. But there was a comment over here by Leo. I don't want it to go way too far because it's related to what we're talking about. And Leo said, the problem is that butane is not a gas in our atmosphere, so this argument is a fallacy. That's not from me, that's for the audience.
Yep, that's a good point.
Yeah, the way I understood, just 30 seconds an attempt. I understood Snell's law big time from my very just normal education. That the light passes through a different medium and it bends. It does an angle, like it goes straight. If it goes straight, it hit a different medium and it just bends a different angle, right? But then Fermat's principle, I just learned it more recently. Fermat's principle works similar to the Snell's law, but it doesn't need a different medium like Snell's law does. Within the same medium, the light bends. It depends on the different density. The more or less density, the light will bend gradually. Not unlike Fermat's principle, it'd be a hard, different. Fucking I lost my words. It would be a hard bend with Snell's law. With Fermat, will be a gradual bend with the light. It's kind of the way I understood it. But I'm mute myself. Sorry to interrupt.
No, that's exactly right, and that's why the butane. That's why it's important to know that the density of the volume area that you saw that effect was incredibly dense, low down next to the butane, next to the container or barrel or whatever it was, and is less dense the further away from the surface of that barrel because it's meeting air. And there is no boundary there. It's just graduation. Even though we might say, well, one's butane and one's air. That's strictly not true. All of it is actually both in the effect area.
Different because of the camera.
Sorry,
the camera's not in butane.
No. Like I say, the boundary conditions of exit and input wouldn't matter because there's no boundary.
Okay, so if light was going from a dense medium to a less dense medium, would it bend up?
In a boundary condition, inside the reflecting angle, you've got to define.
It would bend up, yes.
So listen to me. You've got to define the boundary conditions in this, and like I say, nothing about the boundary conditions are relevant to the butane example.
But you said the boundary condition was a change in density, right?
No.
So what? Sorry, what was again the boundary condition that you said?
So a boundary condition is a physical edge and change. Not, you couldn't say, well, I've got let's say I was able to get a sphere of butane without a container, but it's a solid dense sphere of butane. And then I just press go on physics, which means that butane then spreads out. And the surface of it is not a boundary anymore. Therefore, you cannot actually work out an incidence angle because there's no angle or surface normal to figure that out from. So in the butane example, the only way to say, hey, look, it should have done this because of it's going from less dense to more dense is put a piece of glass over it that's bent, and then your argument is relevant. And which is what I was going to show you here. These are relevant to your argument, these blocks of glass here. But not the butane example, because it's a graduated, non-boundary based effect. But you can still simply say light bends towards the denser medium and the denser stuff will be lower down and nearer the surface, which means light bends along the surface. You can't say, well, there's a boundary condition, and when it leaves it and goes into it and comes out of it, that's not a thing. Because
so let's say I did this and I was a few meters away from a tank and I poured some butane on this object behind a tank. Are you telling me that that's not a boundary condition there? Even though I'm like a good few meters away from it?
Correct.
Really?
Glass, yes. Physicality. You'd have to point. Can you touch it? I mean, you wouldn't need to touch it.
Yeah, you can touch butane.
Would you be able to put, if I gave you a pencil and said, put that pencil nib on the boundary of where you're going to calculate your incidence angle and the surface normal, would you be able to do it?
Well, no, because gas eventually disperses,
there you
doesn't
go.
it? Yeah, but even though it disperses, by the time, if you're only pouring it for a second or two, it's not going to have time to disperse to where the camera is. No chance.
You lose surface normal. Okay. I'm gonna say that this is an estimate, but I'm probably going to be on the conservative side. You would lose the surface normal and boundary condition once you pour it the second it meets the air within the fraction of a picosecond, because it's a fluid, and there is no way that is keeping any boundary saying, hey, this side's butane and this side is air. No.
Yeah, I agree, but for a snapshot second, like if you was to screenshot that second right then when it lifted up and when it was poured, then in that snapshot second, it's not had chance to come to the camera, and you've still seen it rise.
No. So the light is the thing that's changing. The butane doesn't get to the camera, and it's not a depth-based effect. It's a vertical one. So
I agree that the butane doesn't come to the camera. That's my point. So the lights come from the butane into the camera, which is less dense.
No. So what you're thinking, I think I get where the mistake's happening now. You're thinking the effect is based on depth away from you. Yes, and that's light is hitting something.
No, I'm thinking the effect is from the light coming to you, to the camera, to you or the observer, the camera, whatever it is.
Yeah. Either way. Now, the density change is not about perpendicular. So let's take this example here. Yeah. The change is not about perpendicular incident angles, as in to the camera straight out and hitting something. That's not what the change is. The change is based on the vertical, so up and down. The change of density and medium in the atmosphere using Fermat's principle or in a medium is about the vertical. So
you're not saying it's horizontal, like across the Earth, it's vertical?
I'm saying the change is vertical. Density change is vertical. In
so
that
it's not
example
horizontal.
and on the Earth.
So not horizontal, not level, flat, horizontal. No? Not horizontal.
I'm sorry, the density is vertical in the atmosphere.
So it's not horizontal.
The atmosphere stretches out horizontally, but the density gradient is a gradient.
I'm talking about refraction.
Vertical. Sorry?
Is refraction horizontal or vertical?
That's a very weird question.
Well, we're talking about refraction, and you're saying it's vertical, and then not saying it's horizontal. So I'm asking you to clarify if it's vertical or horizontal.
Right. Okay. So I'm saying the density gradient is vertical, which causes the bending of light. Nothing to do with horizontal or incidence angles that are perpendicular to the ground. It's to do with the vertical atmosphere and the vertical density change away from that barrel as well. Vertical.
Yeah, but even on your globe model, it's still horizontal, but then it's meant to bend down to the more dense medium as you drop with curve.
Forget the curve is irrelevant. So the atmosphere,
no, the curve is irrelevant because the curve is what causes the density gradient to change. Because if you was to do a tangent from your gradient where you're at and you was to do a tangent out, then obviously the gradient's going to get less and less dense. So obviously that's why they say it bends down into the more dense medium.
Incorrect.
Why is that incorrect?
That can change the magnitude of the effect, granted. But it cannot change.
So what's refraction on your model then if it's not going horizontal like a tangent and then bending down into a more dense medium?
So it's bending down towards the denser medium.
Yeah, that's what I said. So if you do a tangent, if you was a light and you did a tangent across, and then if you was on a globe, the globe would drop away and drop away and drop away. So then the denser medium would be down and down and down. So in your model, you're saying that it basically goes on a tangent and then it bends down into that more dense medium because the globe drops away.
I'm saying the globe is irrelevant to the fact that we have a density gradient in the atmosphere. That would exist both flat and curved.
Yeah, I agree, but refraction on your model is it then bends down into the more dense medium, and the reason you see beyond the curve in your model is because it bends up, because the light bends down from a tangent into a more dense medium because the ground drops away.
It wouldn't
so then you end up with more
about
dense
the curve. Like I said, the curve will add a certain magnitude to it, but light would still bend down on a flat Earth. That's the example here. If we look at this example, I've got a medium that is more dense lower down on 3 steps. So it's more dense lower down on 3 steps, and it appears that the ground is apparently going up and it's concave Earth. But in fact, it is flat Earth. These are flat boxes. These are on a flat plane. These boxes, all flat. These are them here. But they.
Okay, so let's say you was wrong about refraction and it made light bend out, and it made light bend the opposite way to what you believe. Then obviously with distance, if for example you what you thought about refraction was wrong, and it actually bent the opposite way. It wasn't the way that you say it was the opposite way.
Like
and obviously with distance, things would appear lower.
Yeah. So I tried showing you this earlier. So you see this here? This is it working the opposite way. So
you haven't got none of the atmosphere and things in that, right?
No. So this is taking 3 graduated effects of the atmosphere where it's so this is bending light upwards because the more dense the density is higher. The density bit is more dense higher up. So now light bends upwards, which makes things appear to curve down. So if we look at this blue thing, it's now this is where it is physically on the right, where it
But what
apparently
you
is on
need
the
to
left.
do is make it bend down where it makes things appear lower.
Yeah, this is it. This is that. This is a
So
flat
that's
Earth.
like bending down and things appearing lower.
Yes, this.
Well, that's not what you just said. You just said it was like bending up to a denser
Yeah,
medium.
no, sorry. This is light bending up an object
Yeah,
because of that
well, I'm
appearing
saying,
lower.
can you make it so that it's like bending down to a denser medium, but that things sink into that ground kind of thing? They're lower because they're bending down.
No, light bending down makes things appear higher because it changes the angle that they get to our eye. And
Okay, well, on your flat Earth model, can you make it so that the light bends down and makes the image lower when it bends down? Because that's how actual refraction works, in my opinion.
so you're saying a denser medium.
I'm saying light bends down, which drops the image down. Why would you expect something to go down and then raise it up? If something's going down, it's going down. It's not going to come up. It's like even for the straw example in water. If you look at the straw example in water, you will see that actually that straw appears lower than when it's in the air. And you try and say it makes it appear higher. It doesn't. If you look at that straw in the water, that straw appears lower than what it does in the air.
Now that is something that you can calculate yourself with Snell's law because there is a boundary condition there. You could figure that out.
And when you see it, what happens? You're not in that water. You're not in that glass. You're in air. That air is less dense than water, and that air is less dense than glass. And that's when you see the light come to you. Think about it.
I have thought about a lot of things. Wait a minute, I'm just going to draw something for you because I find I'm going to have to reshare, Jose.
Go for it. Yeah,
So,
go for it.
yeah. So
Let me read this one comment very quickly, and it is by Real Sickness. He say, "As if our models haven't been tested, for fuck's sake." That was a comment he typed earlier.
Just bear with me. I'm just gonna share. Just gotta start a.
Let me holler the audience and everybody watching. We still got 60 plus people watching. I'm trying to get 60 thumbs up at least. That would be excellent. And if you live under a rock and you are not subscribed to Rachie 50, well, go to the description box under this video and find a link for her channel there. Boom. Is that cool, Rachie? Shilling for you. Shilling your channel over here in the description box under my video.
Yeah, that's fine. Thank you, Jose.
Okay. Yeah.
You have to bear with me. I'm just trying to get something that I can sketch on because
some people was asking for your channel, StingRay. I know you got a channel and you got a few clips and a few things.
I don't care about YouTube.
Okay, yeah, there you
go. I've got enough things to do without care about a YouTube channel.
Yeah. When you're ready to share, let me know.
Just apologies. I'm just having to. I'm gonna.
I see you. Yep, we both got you.
That's how light bending down makes things appear higher in vision.
Yeah, but things don't bend down like that, so you don't get a curved line with a refracted ray. It still ends up a straight line. It just ends up higher or lower depending on where it's refracted in.
So it changes
It
the
doesn't
angle
curve.
over the distance.
Yeah, but you've got a curve there. It doesn't curve.
So what do you think changing direction means?
Changing direction. So basically, imagine a light ray coming in horizontal, and then it enters a denser medium or a less dense medium, whatever, and then it comes out that medium at a higher or a lower elevation, shall we say, but it still comes out straight no matter what. If you look up refraction, you will see pictures, and you won't see no curved line. They're all straight, but they come out at a different angle.
So let's say this is something that does it. The object is here, and we're looking through this. This is the medium, and we're looking through it. So a straight line comes up here, hits this, and because it bends downwards, it does that, which now means this object appears here because of those angles in the tangential change.
Okay, now would you agree that where the eyeball is less dense to where that square cube thing is?
Yeah, well, yeah, if you want.
Yep. So okay, when it's come out of that cube thing, what have you done with that angle? You've bent it down. Now, what do the mainstream say about bending down? They say it bends down in a more dense medium. When you've just agreed the square is more dense and the eye is less dense, so you've bent it down into a less dense medium again.
Right. Okay. So here we go. This now, because you keep going on about these boundary conditions. This now.
Yeah, because it's important. It's a change in wave speed, and the change in wave speed causes refraction.
Yeah. So here we go. This is the density gradient now. The eye is still on the left. This is the density gradient. So I'm going to do it. I'm going to do it based on boundary conditions. Yeah. So here we go. So this is the object. It's in fact, wait a minute. Let's place it a bit lower down so that I can do more shit. Right, there we go. So that's the object, and this is the density gradient. We've got high density here. We've got low density here, and this is the same throughout all of it. A single photon leaves and hits here. It then bends slightly down. It then bends slightly down even more. It then bends down.
Wait. So you've put the photon and then you've drew up instead of drawing straight across. And not only that, you're saying it bends down, but you're still bending it up.
No. This is the direction that the photon is leaving.
Yeah, but you're bending it up. That's not down. That's up.
No. In the atmosphere, this is what happens to a photon that left in this direction.
So it bends up.
No, it leaves.
But you're bending it up right now. That's up.
Okay.
That if you look at that if you look at the bottom line, that's low. If you look at the top line, that's high. You're going up.
Okay. So how about this? How about I have this object and it emits in every single direction photons. How about that? Yeah.
She got you, StingRay. Yeah. She got you.
Yeah, I know. So imagine. Well, don't imagine. Can we agree that this emits bounce light in every single direction? Yes or no?
Yeah.
Awesome. So what we have now is if there were no atmosphere, this would appear exactly where it is because the angle that it hits the eye perfectly reflects where it is, correct?
Yeah.
Awesome. Can we agree that in the atmosphere it's denser down here than it is up here?
Yep.
Awesome. Can we agree that if something left horizontal like this, that it would bend towards the denser medium and not make it to the eye? Is that fair to say?
Correct, yeah.
Now, what about if we take the one that's firing a little bit higher? Is it fair to say that if I drew this line and did this, oh shit, that missed as well?
Yep, that's what they say, yep.
Awesome. Now, if I choose one that's actually pointed a little bit further up like this, and it goes like this, and it hits here at this angle, is it fair to say that the incidence angle here reflects its apparent down position where I'm going to see it?
No, you lost me. No.
Interesting. I don't know where the disconnect came from there.
The disconnect come from you drawing it higher and drawing the line going straight across.
Okay,
like
I'll keep drawing these then. How's that? And then how's that? And then how's that? Oh, we're just starting to hit it there. And then how's that? Oh, right, we're hitting it there.
Yeah, that's fine. No, that's not fine. No. That's why you've lost me.
There's a disconnect there, right there. Yeah, the apparent position. Yeah.
Okay, so let's think about. Oh, okay, so if I've lost you on that, let's simplify this a bit so that we get to the bottom of it. So can we agree that if light, so this is our eye here. I'll just draw a surface a bit further out. So can we agree that it is the incidence angle here that shows us where something is? So if a light ray came in here and hit at this angle, that I would perceive something here. That's fair to say, right?
Yeah, probably, yeah.
Yeah. And same if a ray hit at this incidence angle, I would see something here, correct?
Yeah.
Now, here's a question. Now, if light hit here like this, that and then went in, that I would see something apparent in this position. Yeah, let's say something was blocking it. Right. Okay. Now that I've got that, can we agree that if an object is emitting omnidirectional photons due to bounce or reflecting light, and it doesn't matter what that object is, it could be, draw anything here, that if it's bending towards the denser medium, and we've got a denser medium of 14.7 psi down here, and let's say, for the sake of argument, 13 here, because we're doing it over great distance and great elevation for some reason, just so that there's a big number difference, because there wouldn't be in reality. There wouldn't be a big number difference. There would be a density difference, but there wouldn't be a big number difference. So light's been emitted all over, but each one of these directions is going to bend according to Fermat's principle based on this graduation of density change between these two in a vertical fashion. So what that means is this ray starts to bend down and hits at this angle. Now, I've only done it gradually, but this angle means that if I extend this out, this is where I'm seeing that object now relative, because it's hitting at the same place. My brain is saying this is where that object is and that's where that corner is. Just the same as it would be, someone wanting to spear a fish.
These big lines in the left-hand side, is this like the eye, representing the eye?
Yeah.
Okay. And then the one in the right-hand side is just the object emitting light. Right, got it.
Yeah.
I'm mute, I'm sorry. Just wanted to understand myself.
Yeah. So this single ray that left in this direction bent down and hit at this angle. Now we could have an infinite amount of rays that fire like so, but they're all going to follow about that path and hit there like so, and they're bending down.
So my only question is, how come you see there and not follow the ray back to the actual object?
Because the only thing that matters is the incidence angle here. So I don't see where an object is. I see the angle of light that hit my eye. And that angle is in my brain is perceived as being straight. I mean, in all seriousness, you can perceive like I've got astigmatism in my eyes, or a slight stigmatism, which actually means my eye shape, my lens shape. I mean, this is a massive exaggeration, but kind of pear-shaped, to be fair. Now, it's an amazing thing. What actually happened with me is I saw the world like everybody else saw it, but my brain was doing hellish corrections, which gave me massive headaches. So now I, using Snell's law, thank God, have glasses that correct for that. So the only thing that matters is this incidence angle, and you can test this with a magnifying glass as well. It's the same principle, because a magnifying glass has a different curvature, which means when something comes in like so, this incidence angle, and obviously refraction, it actually leaves at a harsher angle because of the surface normal, which actually means it magnifies. These are all how we build magnifying glasses or lens elements or anything like that. And it's the same way that the human eye works. So because the atmosphere is denser lower down, less dense higher up, and light does bend. But by the way, something like I said to you before, a ship over the horizon, to bring it back at 8 miles, you need to bend it less than 0.1 degree or something. And that would bring loads of it back. Or, on a curve.
The problem is with saying 1 degree is 1 degree is different depending on what the size of the circle is, pretty much. So I could have one circle which is small and one circle which is huge. 1 degree on the huge circle is going to be a bigger degree than 1 degree on a smaller circle. So when you say it only needs to bend 1 degree, well, 1 degree is a lot on the Earth model.
Yeah, I get it. So I don't need. So when I say 1 degree, I'm on about source tangent versus destination tangent. I'm on about the difference between the vectors A and B, which in this case would be that. That's what I'm on about, being like whatever degrees. The distance I haven't specified, but like I say, something at 8 miles, we only expect to see like 0.1, 0.2 degrees bend of light. And
the problem is as well, you've put your sun or your object, which is omnidirectional, you've put it like really, really low. What happens if you put that high?
Oh yeah. Okay, so let me do that for you. Right. So now, if we've got an object up here, what we'll do is we'll say I'll do one ray that won't one thing that won't hit. So this leaves here and goes and misses the eye completely. But leaving this tangent doesn't miss the eye and hits here. Now,
okay, so the first one that you drew, just to stop you a second, that first one that you drew that you said missed the eye, would you see light? Would you see, nighttime, daytime kind of thing? Would you see the sun if it missed your eye?
No.
No. So therefore, could it be daylight or nighttime, shall we say? So could it be sunset kind of thing?
So this isn't the sun. This is just an object. It can be the sun if you want it to be. But
I'm just imagining it as the sun, and if it didn't come to your eye, then would you see? Would it be daytime kind of thing?
So the important thing here is I'm choosing one point on this, the bottom left. Now we can say that 1 quintillion photons are reflected from this point outwards in every single direction. That's it, every single direction. Now, if all I'm dealing with is that tiny infinitesimal micron of the bottom left of whatever this is, the sun, an object, a car, a boat, I don't care. Then what I'm seeing is this. I've got rubber on. Then what I'm seeing is the incidence angle here, if I extrapolate this out, is there. Which means now I see that bottom edge here, that bottom corner. So we've gone from here to here. So this is the physical position. Ooh, that didn't look like a P. Physical position and apparent position. It doesn't matter what the object is. Could be the
and what evidence do you have that is actually the case, though, that is how reality works, that the light bends and then makes it higher?
A magnifying glass.
That makes it bigger. I wouldn't say it makes anything higher.
So let me draw this for you. So a magnifying glass is an absolute demonstrable example of this, because what we've got, and Snell's law, to be fair. So what we've got is, I'll draw it. Wait a minute. How am I going to draw this? I'll draw it this way. So I've got this, and then I've got that. Now, I've got more curvature on one side than I have the other, right? Makes sense? So now...
Yeah, the only problem is that you're drawing, like, how is this evidence because you're drawing something?
I'll just explain to you how a magnifying glass works. You can go out
and I know that, but I asked you if you had any evidence that that's actually how Snell's law works, that actually, it bends down, which then makes something higher.
With a magnifying glass, it'll make something bigger.
It'll make something bigger. Yeah, I agree with that. It makes something bigger,
Bending
but
light.
will it make something
Yeah, that's
higher?
bending.
Is what I'm
That's
asking.
bending light. Yeah, that's bending light. So if we think
Yeah,
about
but do you have any proof of that?
yeah, magnifying glass. So if you think of this as the
You
top
keep
and this
saying a magnifying glass, but do you have any proof that it bends into a denser medium, making it higher?
well, I can find a magnifying glass for you if you want.
Well, that makes it bigger. It doesn't make it higher, does it?
Right, so in this lens element here, we've got the top and the bottom. We've taken a slice of it now about what happens in the thinnest slice of it. That's all we're interested in. So we've got a light ray to figure out what happens. And on this side, we've got a subject. We've got light that comes in, the incidence angle here. And because it's a denser medium, it actually wouldn't do anything at this angle, but it would exit like so. Now, what that has done...
Hold on. How did you get that?
Normal, n. So the normal of the ray.
Yeah, but you've bent it down and then bent it up.
Yeah. So you did. So
okay. Why did you bend it up?
Because you're leaving at the same tangent.
So you're leaving a denser medium going into a less dense medium.
So this is 90 degrees, and this is.
So when we did that previous thing, and it went into a less dense medium, you didn't bend it up then, now, did you?
No. This is we're on about boundary conditions now. So this is 90 degrees.
No, we're on about the same thing. We're on about refraction, right?
Refraction in Fermat's principle is something different to what I'm showing you right now. So we've got 90. One is graduated in a non-homogeneous or homogeneous but gradient density-based medium. The other has boundary conditions, of which I'm showing you right now. So the 90 degrees
is the atmosphere homogeneous and whatever the hell you just said?
The atmosphere, we can think, you use Fermat's principle to calculate refraction through the atmosphere. So we've got...
Is it homogeneous in what you just said?
No. The atmosphere is non-homogeneous fluid dynamics. If you want to simulate it, you use Navier-Stokes equations. But let's just deal with this at the moment. You wanted to know how a magnifying glass works or how I'd use it as evidence.
No, I didn't want to know how it works. I asked you for proof that Snell's law actually bends into a denser medium, making something appear higher, and then you just said magnifying glass and then started drawing. What I asked you was for evidence or proof of actually things going into a denser medium appearing higher, but all you're doing is drawing. Drawing is not proof or evidence. Drawing is just an explanation. An explanation is not proof or evidence.
Absolutely. Drawing is not proof. I'm explaining to you how a magnifying glass works so that then if I go and get one, I'll say, hey, look, this is how it works and this is what's happening. So this 90 degrees exit and entry means that here we have the same thing. This is how collimation of light in a lens works as well, with convex or concave lens elements. So what we've got here is for the same object, here it got bigger, apparently. That is magnification based on Snell's law and incident angles exiting and entering denser mediums. That is how a magnifying glass works, and it is bending light up if you take the center slither and call one the top and call one the bottom. That's a magnifying glass. I'm actually in the middle of a house remodel at the moment, so I won't be able to find a magnifying glass.
So what you're saying is it bends at the top, it bends, or what you could call the top on here, it bends into a denser medium, then goes down, bends into a less dense medium, then goes up, and then bends down into a more denser medium at the bottom, and then bends down into a less denser medium at the bottom. That makes no sense.
Say that again.
So on your picture here, you've got top, and then you've got an incident ray, a ray coming in, hitting a more dense medium, the magnifying glass, exiting the more dense medium into a less dense medium and going up. And then at the bottom, of what you've labelled the bottom, you've got the ray coming in, entering the more dense medium, bending down, and exiting the more dense medium, entering the less dense medium, and still bending down.
So
that's what you've got right there.
So the light here, I choose parallel rays so that we didn't have to deal with this. The only thing we deal with is surface normal.
Yeah, but what you've done, at the top you've got it bending up, and at the bottom you've got it bending down. How does that work?
Rachie, the fractional reduction in light speed here is in a straight line. It's a
Yeah, but
straight
one's going up,
line.
one's going down. Why? Explain that. Why is one coming out and going up, and one's coming out and going down?
The normal surface direction. It entered here at 90 degrees. It will exit here at 90 degrees to the surface normal. But the surface normal is a different angle here because it's bowed out more on this side than it is on the other. This is how lenses work, magnifying glasses work, everything works.
So it doesn't matter about more dense and less dense medium then?
This is not an example of that.
So what's the point in bringing it up when we're talking refraction?
Because this uses refraction to magnify things.
So it is an example of that. So why is it going up on the top and going down at the bottom when it's entering a less dense medium after it exits the glass?
There is no change in angle in this because the incidence angle was perpendicular.
What do you mean there's no change in angle? Look at your picture. How can you say that's not a change in angle?
To the surface, Rachie. To the surface.
The surface of what?
The glass.
Yeah, the surface of glass. Okay, so we look at the surface of glass, we look at the top, and we look at the bottom. Are you telling me that top angle where you've got an N and the bottom angle where you've got nothing on it is exactly the same? Is basically parallel? No, they're not.
You're right. I'll give you that. They are not parallel because 90 degrees at the surface tangent here and there are not parallel. Hence, they diverge. Hence, we get magnification, a very well-known effect with a lens element like this.
But I still don't understand how that's got to do with refraction and making things higher or lower. All you doing is showing me a magnifying glass, which apparently makes things bigger. Okay, I agree with that. Magnifying glass makes things bigger. Yeah, I agree. What's that got to do with refraction and making things higher and lower?
Right. Okay. So this item here, yeah. If we're looking at something from this side now, we're looking at something, and we are seeing an object here. Where do you think we're going to see it? We're going to see it here. Because the only thing we care about is the incidence angle that goes to a lens, and that is it.
Okay, I would agree with that, except when light goes from a more dense medium to a less dense medium, what happens?
Depending on, well, give me the variables. We'll calculate it.
I'm telling you, more dense to less dense. What happens? What way does it bend?
You'd have to actually tell me the. You know, you can have such a thing as total internal reflection. You know, if it hits perpendicular, it does nothing. You have to tell me the graduation density, and then the surface normal directions. You can't just say it bends. You can infer Max principle in a vertical gradient.
Okay, let's imagine a flat Earth, for example. Okay, it's flat Earth. There's a density gradient on flat Earth.
Yay.
And then the light enters into the medium of flat Earth, and then it goes from a more dense to a less dense medium. So there's high pressure somewhere and low pressure somewhere. It goes from the high pressure, the more dense, to the less dense. What happens to that ray? Does it go up or down?
Wait a minute. Are we talking about? So if I've got a flat Earth, are we talking about it? There's like you're on about if this is a high area, what happens to the ray?
Yeah, if you got a high pressure and a low pressure, so you got a high density and a low density, and then the ray goes from the high density into the less density, or from the high pressure into the low pressure, because obviously pressure affects incidence refraction as well. So obviously that's going to have an effect on refraction. So you got high pressure, you got density, you got all these different things which have effects. All I'm asking is, if it's going from a high density medium, if it enters a high density medium, then leaves into a less density medium, what happens?
Yeah, but you're talking about a lens element there. If you're talking about a pressure system like this that's high-low, whatever this is at this side...
I'm not talking about lens. I'm talking about how it appears to anything, a camera, an eye, anything, a dog, you know what I mean? It doesn't matter what that eye is, but how it appears to that thing that's observing it when it goes from a more dense into a less dense.
Yeah, but you again, give me the boundary condition if you're wanting me to calculate it using Snell's law. If you're on about an environment like this, this would look like the world's most freaky mirage looking through it. It would look like a portal to another world if it was bending the light a lot. This
What
is
do you mean,
not
a
the
portal to another
atmosphere.
world?
Lateral boundary condition. Let's just stick to Snell's law and say it describes the atmosphere. If that is the case, you keep going to lateral changes.
But would you agree that when you have a high pressure
let
system,
me
you
just
have a
finish
high
this.
pressure in the middle, and then around it there's a low pressure system,
Let me
exactly
just
like
finish
you've
this. So you're going to this. You're saying this is high, this is low, and let's say these are medium. You're going to this condition. This is nothing to do with the atmosphere. This is what happens inside a camera.
So we don't have high pressure and low pressure in the atmosphere.
We have it all over, but we don't have it in conditions like this.
And high pressure moves to low pressure, which causes wind. So we do have high pressure and low pressure. We have high density and low density. And all I'm asking you to answer is what happens if a light goes into a more dense medium and enters into a less dense medium. And for some reason, you can't answer that.
Yeah, what's the answer? So give me the normal directions.
All I'm asking you is, you say, for instance, if I says to you, if light enters a less dense medium and then goes into a more dense medium, you would say straight away the light bends down, which raises an image up. Now, all I'm asking you is the opposite. All I'm asking you is if it goes into a more dense medium and enters a less dense medium, what would happen? And suddenly it's, oh, I need to know the bend rate, I need to know this, I need to know that. But when I tell you that, oh, it enters a less dense into a more dense, suddenly, oh, it bends down and we don't need to know nothing. But when I tell you that it enters the opposite way, so vice versa, suddenly we need to know everything.
Right, are you ready, Rachel? This is an incredibly high density and everything around it is low. Light
that's like a high pressure system, yeah.
Yeah. Light enters like this. Can I ask you, what do you expect that to do?
I expect it to enter the high denser medium.
Yep.
And then for me, I'd expect it to enter the high denser medium and it appear lower. But to you, it would enter the high denser medium and then it would appear higher because you see things higher.
Don't assign me anything. So what happens to this angle?
The mainstream, I mean.
Yeah. So does it go up or down, this angle?
For me, it would go down. For you, it would go higher. Up. For the mainstream, it would go up.
We'll do both. So you're saying... Oh, wait a minute. So you're saying... wait a minute. Is yours the one that goes down? Well, I won't answer. Just give me yours.
Well, mine would go across into the high denser medium and then go down into the less dense medium.
So it'd go like this?
Into the less dense medium, yeah. So it got up in the higher density and then it leaves that high density, it go down.
Yeah. So sorry. So what you're saying is yours would go up to begin with, like this.
Yeah. And then down.
And then it would go down or leave at the same
down,
thing?
Yeah, into the less dense medium, down.
All right, so it'd go down like that.
Yeah.
Okay, awesome. I suggest you don't drive because your windscreen would fuck you up.
I don't drive.
Because looking through your windscreen, I'm not sure you could tell where anything was.
Why?
That's higher density than the air inside and the air outside. I suggest you don't go driving, please.
Okay, so with the air and the glass and everything that you just said, you don't think there's no refraction there?
I didn't say that, did I?
Well, you're saying you don't think I should drive, which means that I think that something's in a different position to it should be. And if there is a refraction there, then obviously it's in a different position to it should be. So obviously you're either saying there's refraction there or you're not. What is it?
So define what refraction is for me first. Let's make sure.
Change of wave speed.
Right.
Change of wave speed.
So there is refraction here then, yes, I agree.
Yeah.
So what actually happens when I look through my fucking window is
there's a change of wave speed.
The light comes in here, and because of the incidence angle, it stays the same angle, but reduces in speed. And then based on that angle, exits at the same angle. We call that a window.
No, because the changing wave speed also changes direction.
No, incorrect. That requires normal and incidence.
So how do you change wave speed without changing direction? So say you was in a car, for example, and you're pretending to be the light, you're an analogist.
It's a mirror, like here. It's a glass window, exactly like a glass window.
And you have to change wave speed and you have to change direction in order to change wave speed.
Correct.
Correct, yeah?
So that would mean looking through a window.
Correct.
That means looking through a window. That means looking through a window. It should move things all over the place then.
Well, it should do according to Snell's law, yes, but it doesn't, does it?
Explain to you that normal direction and incidence angle are incredibly important. Not just the fact that this has an IOR of 1.55 and that this is 1.03, as in air and glass. No, that's not the only thing. That's so not the thing. Otherwise, Windows would fuck you up.
I agree. And people say when light goes from a more dense medium to a less dense medium, as in entering a glass, that a refraction occurs. Now, I look out my window, there is no refraction.
So
Explain that.
So refraction, we defined it. That's why I asked you. You said the reduction in wave speed. I agreed with you. Is there a reduction in wave speed here? Yes, there is. It's inside the glass. Did that change direction? No.
So how can it change speed without changing direction?
Really easy. It just slows the fuck down and carries on in the same direction.
That's the thing. No, light doesn't slow down. If you actually Google it and look at what Google actually says about it, they say it doesn't actually slow down. What happens is they call it slowing down because it actually changes direction. So it takes a longer path. And if something takes a longer path, then obviously it takes longer. So technically it slows down. That's what they say.
So we've established that glass from air to glass to air doesn't change direction, or else when
we've
you
established that glass should cause refraction but doesn't.
Glass does cause fractional reduction in light speed during.
But when I look out my window, I don't see no refraction. Do you?
I see refraction every single where I look, unfortunately.
You're going to tell me next if you hold your hand in front of your face, that's not your real hand, right?
No, my hand is my real hand.
Yeah, but they say refraction means it's not your real hand, in which case I tell them to stab it because that is your real hand, and you calling it refraction and saying it's not your real hand is just silly in my opinion. Because if you, like I said, if you look out the window and you look through the glass, you don't see refraction. I don't see things higher than they should be. I don't see houses like I don't see houses, you know, a mile in the sky or a few meters higher than what they should be. They're in the place that they should be.
Yeah, well, that's because it isn't predicted by anything of modern science that it should be if the surface normals are the same. The surface density.
Surface normal.
So a surface normal is just perpendicular vector to the actual matter. Yeah. So on the glass panel, the surface normal, no matter where you hit it, are parallel vectors which are perpendicular to the surface.
So if I had a horizontal line perpendicular, it would be vertical, right?
Yes.
But when they say that light's vertical, like perpendicular to the ground, they say that there's no refraction, but that can't be true because the light's coming in and entering a more dense medium.
Just like this glass, it entered a more dense medium and didn't change direction, just slowed it down a little bit.
Which should cause refraction, right?
It causes refraction if we define refraction as the fractional reduction in light speed due to a density differential, then absolutely it causes refraction. If you define refraction as making something appear apparently different significantly than where it should be as to fuck your mind, then no, that's a different type. That's the effect of refraction.
So you've got two definitions for refraction?
No.
Well, that's what you just said. You just said two different things for refraction. Refraction should be one definition. You've just gave me two.
It's both.
What do you mean it's both?
I mean, there can be 0 to a lot of change in apparent location.
I agree that the magnitude of the effect can change, sure. But what I'm saying is refraction should be one definition. You're giving me two right now.
No. Okay, I'll give you two elements. I gave you two elements to the definition of refraction. 1, fractional reduction in light speed. 2, a change or perturbation in the apparent position of what something should be due to being exactly the same at 0 all the way to a fair bit. How's that? The
change in position is because of refraction. Agree or disagree?
So is a fractional reduction. So is a reduction in light speed.
So you're giving two definitions, but your second definition is the cause or the effect, shall I say, of the cause of the first one.
Two aspects to the same thing. I'm describing refraction.
Yeah, and the second one is a change in position, which is caused by refraction, right? So technically, that's the effect, not the cause.
All right. Let's look at this. Can you tell me what an incidence angle is?
It's when it bounces off something and changes angle.
No, we call that reflection.
Yeah, and the incidence angle is where it enters that. Basically, you enter the denser medium and it changes angle. It's refraction, the change of wave speed.
Right.
Essentially.
That we call reflection.
Can I interrupt
Reflection.
for 1 minute? It's going to be kind of a quick thing before we move on to these definitions and stuff. I got a few comments, just 3 comments I want to read quickly before they go too far. First of all, C4 says, "Man, StingRay is getting wrecked." Wah, wah. He's crying about it, man. StingRay, you getting wrecked, bro. Leo, thank you, sir. YouTube links video and what StingRay is saying. I think that was earlier. You asked probably a few questions about the laws or perspective.
For evidence, yeah.
So Leo said that YouTube links videos and what StingRay is saying. He's happy with that. And then John Rapp says, "Rachie, stop picking holes. Explain it yourself." Thank you very much, gentlemen. Appreciate the super chats.
So really quickly, we've got incidence, normal. We've got index or IOR, which is the index of refraction.
Okay, can I ask you one thing about that? Index of refraction. Yeah.
Oh yeah.
How did you get the index of refraction without knowing the one-way speed of light? Because obviously the index of refraction is basically based off the one-way speed of light, which then changes based on medium. So where did you get the one-way speed of light?
We measure it.
You can't do that because of relativity. So how did you get the one-way speed of light?
So we measured it in a vacuum from point A to point B.
No, you can't do that because of relativity.
You
move
point A to point B to
point B.
Yeah, from point A to point B.
You can only measure the two-way speed.
Correct. We can't measure the two-way. We have to measure the two-way speed of light, but there is no evidence whatsoever to say that it would be a certain speed in one direction, and it doesn't change anything.
So you're using an index of refraction, which you can't even get the one-way speed to determine that one-way speed, to then determine the one-way speed in a medium, to then do the division, to then get the index of refraction.
So if the two-way speed of light was a thing, it would also be a thing inside of a denser material, which means the index of refraction would still stand. It would not change the timings of what we read. It would just be really fucking interesting and weird, but no one's ever proved that. It's a speculative thing and was put out there as a postulation because it's not provable. So, no, it doesn't change.
I agree with that. It's not provable. So if it's not provable, you cannot use the one-way speed and then divide by another slowed down speed in a different medium, because that one-way speed wasn't even confirmed to begin with. Would you agree or disagree?
Disagree.
So the one-way speed is confirmed according to you?
No, but for all probability...
So then you have to agree then, don't you?
No. If you'd let me finish. For all no, do you want to let me finish? Yeah. So we deal with the thing is there's no clear-cut yes no. Science or our system of how we deal with things is not binary. There's no such thing as absolute truth in my world either. There's only...
I agree with that, but do you agree that, let's say, maths is proof?
Let me finish. So maths, do you say maths is proof?
That's what they say. Maths is proof.
There's certain things in maths that can't be proved, but let's say basic or fundamental math is it can be proof, yeah. So the important thing there is I deal with statistics and probability. That's it. That's how we all interact with the world. It doesn't matter whether someone says, "Hey, I proved this, and look what I did." There is a degree to which you believe them, and then one which you probably don't. And it's never binary, no matter how much you think it might be. And there's always a possibility you're going to be wrong. Now, when you ask me, because I use the speed of light day in, day out. I work with LiDAR sensors at the moment. So, yes, I deal with the speed of light being a constant in a vacuum. Absolutely 100%. And does it work for me? Absolutely every single fucking time. Just like a globe and a sun and a rotating globe does. Every single time. Now, until someone or something says, but look at this, and I try it and I think, Jesus Christ, that is weird. That will break down my probability system that so far, statistically, has been 100%. So it does not matter.
Okay, have you tried changing the speed of light, like a fraction, like a 1%, 2%, 3%, and seeing whether that changes the results in any way, shape, or form?
Well, with the LiDAR sensor, it would be with the measurements that I'm using, it would be. So I deal with my accuracy is probably down to about a distance of a meter, anywhere from as accurate to a millimeter to as inaccurate, about 1 to 5 millimeters, let's say. Changing the speed of light 1% would send that off by a factor of maybe 600,000, I think. So something that would be a meter away would be the length, the radius of the Earth away. So no, that wouldn't work very well.
Okay, point taken. But you still haven't measured the one-way speed of light to determine the index of refraction. Until you do that, you cannot even use the index of refraction.
So I'm going to ask you a question now, and it's a logical question. Ages ago, I'm in a cave, and I figured out that friction creates heat. I figured out that, well, hang about. Oh my God, if I keep going at this, there's fire. Now, that fire is an effect, and it allows me to perform things. Guess what I can do now? I can light in dark. I can cook meat. I can ward off bigger things with the red flame or the red flower. It's fantastic. Do I need to know in a physics sense that that's a chemical reaction or the finite details, or can I just use the fucking thing?
You can use the thing, yeah. But the thing is the thing. You've already got it. It's already a physicality. It's already proven it's there. It'll burn you. It'll kill people. So on, etc. With the speed of light being a one-way direction and the speed of light in that one-way direction, you have not got no evidence of that, no proof of that, no physicality of that. You've got nothing.
So all I've got is the fact that when I use it based on what they say, it's 100% correct 100% of the time and gives me correct readings. I do not care if if there's some magical pixie altering things. It's 100% fucking useful 100% of the time. When it fires an infrared ray out and hits something and returns based on the timing, it's millimeter accurate. I do not give a shit that we haven't measured the two-way speed of light. It wouldn't make a difference. It all still works.
Like you say, but I haven't actually done the maths of that. But it doesn't matter until they actually measure the one-way speed of light. You can't say that is what it is until you measure it. Like if I was to say something and make a claim and say this was such a speed, you'd expect me to prove it. You wouldn't expect to just accept it based on what I said, especially if you couldn't measure the one-way speed of it.
So you remember what I said about statistics and probability? So let's take.
Yeah, that's more quantum mechanics, though, isn't it? To be honest.
So let's take. I actually don't care. Let's take something like my globe Earth model, where all I do is rotate a sphere.
Can I do my 1 minute interruption before you move on to this example of the global model? Yeah, appreciate it. I'm trying to not interrupt in between, the back and forth. 3 comments. Thank you, appreciate the support, everybody. This is Earth is Life. Can Rachie please stop interrupting StingRay? I say Rachie sometimes. Don't, no disrespect. It's just my accent. Come on. Can Rachie please stop interrupting StingRay, Rachie? What the hell?
Sorry.
John Rapp says, for fuck's sake, light does not actually slow down. Look it up. Any thoughts?
Yeah, it's meant to change direction.
Well, yes, but the surface normal is the thing.
And one last comment. One last comment. Tiny Captain says, hats off for StingRay to be able to keep his calm. Thank you very much, everybody. Go ahead, guys.
Not
Yeah.
bad. I'm just going to share 2 seconds just to demonstrate a point, Jose. But then I might have to go to bed because it's getting late. Although it's a weekend, so it should be all right, actually. So I don't know whether you've ever heard me talk about this, Rachie, but this is not a declaration of truth, this model, if you're looking at it now. Absolutely not a declaration of truth. All I can say about this is, given the current information, the distance, the size, all of that, it works 100% of the time, all the time, and gives me accurate predictions and is 100% useful. And by that, I mean, you know, if I wanted to learn when to plant crops and stuff, and I didn't want to do it statistically, I could work it out from this. Or if I wanted, like I am going to do, hopefully have solar panels fitted, I can figure out the angle of those solar panels based on this model, which is actually one of the primary reasons why I created it in the first place. Spoiler alert, England's not great for solar panels during winter. But it works 100% of the time. Now, I do not know that we live on a planet, a sphere. I do not know that as absolute truth. But in every single decision I make, I can assume it to be true with little consequence because it's always been correct so far. Now, that's not to say that if someone came along and said, what about this? Then if that, whatever that was, this, changed something and could have adverse effects, then I'd be very interested. But I can't see how that would happen. So even in you saying, well, we haven't measured the two-way speed of light. Well, that's brilliant, but it doesn't change anything for me. I still use a LiDAR sensor, and it's still incredibly accurate given the constant speed of light in a vacuum measurement that we have. And until someone says, but because of this, it's incredibly wrong, I'll still be like, well, actually, statistically, the 100,000 times I've used it, it's not been wrong yet. So this is weird. How would it be wrong? So even though I agree with you, light could slow down in one direction, speed up in another, doesn't actually make a difference because the return time still works for a LiDAR sensor, still works for everything else and changes nothing. It's still 100% useful 100% of the time. Just as is this globe model by simply rotating it.
Can we start doing some kind of, a little back and forth on kind of final thoughts, more interactive final thoughts, on StingRay? Have you learned anything from Rachie? Did something click on you that changed your perception on things? And same question for Rachie. Did you learn anything from StingRay? Did it change anything, the way you perceive things? Not final thoughts, but maybe kind of one last solid statement. We'll start with Rachie because you kind of had your saying there. So we start Rachie and then StingRay, and then we do the final thoughts to tell everybody to go home and go to bed. It's almost 3 hours long. It's almost 3 hours. I'm happy to stay a little bit longer. What do you guys think? I think StingRay is too late for you.
It's very late for us here, so we need to.
Yeah, Rachie, kind of the first. We got 2 rounds of final thoughts. First round, so far the conversation. What do you think? Any final point that you want to maybe kind of wrap up before we do the final thoughts? Go ahead.
Well, to me, I think it's just, I've learned a bit about different things from StingRay, but like when he tries to say that like it enters one medium and then another, he seems to always ignore the less dense medium. And then when I say, what happens if a light enters a less dense medium and then put into a more dense medium, then suddenly, oh well, it bends down light and rises up. But then when I ask the opposite question, it's like, oh well, I need you to define certain things. So then it seems a bit of a double standard.
I'll respond to that.
Yeah, please.
Yes. So an important thing there is halfway through, I realized you were talking about a lateral depth-based effect that you thought was happening, which is then why I wanted boundary conditions. I realized you weren't talking about a graduated atmosphere where a ray is traveling parallel along the ground and going down due to denser medium underneath it. You were talking about it passing through a denser medium in kind of a a lateral sense. That's why I changed what I was asking for there, because the questions are different then. One is a graduation where it bends down a fraction of amount based on the density gradient, and the other actually then would deal with, well, what are the boundary conditions of those? Are there any? Because you were saying, it's a straight thing, and I think I demonstrated, or I think I gave you the example of your mirror, or sorry, a glass window. That doesn't do anything. Yes, it can slightly change the elevation of things based on angle, but something that hits at 90 degrees leaves at 90 degrees. Well, leaves at 90 degrees to the surface normal, which is what I was on about. And I am actually interested though, Rachie, in your I've actually enjoyed this, even though this still isn't a debate to me. But I'm interested in if you could sketch out what you think the Earth looks like, the flat Earth looks like, and the shape that you described with the north and south. I would actually be interested in that, to create a create a visualization of it.
It would probably help you if I said it more. It is more like an oval, so it's fatter in the middle and skinnier on the end. So almost like a symbol of infinity, but fatter in the middle. So like an oval, pretty much.
If you just find a shape that it looks like, and would the pole still be in the middle, and the North Pole?
No, in the middle? See, you'd have south one side and north the other. So when you're in the middle, you would see different star trails because you're in the middle, which would be technically the equator. But you've got north one side and south the other. That's why that's why I imagine when the sun circles one side, you end up with 24 hours darkness, the furthest away from that, and then vice versa, the opposite way.
Yeah, that's the bit I'm breaking down on. If we could just sketch like the simplest little drawing, then I could probably put it together. Or if we have another conversation whereby I can just model it really quickly.
In real time. Yeah, wing it in real time.
Yeah.
Get it into a 3D. That's awesome. Hey, I enjoyed this a lot. Actually, I did. I try not to interrupt. I let you guys. I have fun. I'm reading the chat box. A lot of new people jumped in. I appreciate for those who shared the show around and they saw your name. The audience follows you, Rachie. No matter what side they're on, they said, "Oh, Rachie's there. Let me see what she's saying." So that's really cool. I appreciate you supporting the channel because you pop in the chat box, you share my show and all of that. I thank you for that. Do your final thoughts. Tell the audience where they can find you. Shield your channel. Anything that you want to say, and we'll get out of here, and then we'll go with StingRay.
Okay. I just want to say thank you, Jose, for having me, and thanks for StingRay for the conversation and obviously the back and forth, and the opportunity to learn different things from him and to exchange points of views.
Thank you very much, and find the link to Rachie50 channel in the description box under this video, and go over there to some of her videos and leave her some feedback. Try not to be too nasty and too dirty, guys. I mean, I think Rachie allowed the responsible trolling in her comment section and in the chat box. I seen her, just shake away, like shake it off the troll, the people that are more like hardcore. Responsible trolling is okay, so people try not to be too direct and don't insult people. Kindness go a long way, like for real, have fun. They need to be triggered and personal about all this kind of stuff. Thank you very much, Rachie. I really appreciate it. And don't be a stranger. I hope one of these days you jump in one of these regular everybody all in, the hangouts, and we'll have a little fun with those. The StingRay, your final thoughts.
I enjoyed this. I've got a new idea for flat Earth if I can figure out the shape that Rachel's on about, which I will build into my my flat Earth model, and put the orbits in as well to see if anything can work. And I'd be interested in that anyway. The only thing that I'll say is I'm not a scientist. I'm not a physicist. I'm not a light expert. I'm not a lens expert. I just like playing around with 3D stuff and like statistics and probability. And the probability and statistics so far show 100% we're on a sphere, and show 100% we understand refraction and Snell's law, and to the main extent Fermat's principle, because we rely on it on a daily basis for lenses. We rely on it in optics so much. The model that I've got up on screen right now works 100% of the time, all the time. It is not absolute truth. It just doesn't fail. That's the only thing. So do I need to understand everything about it? No. I can just use it for beautiful, very accurate predictions that never fail. Cheers, Jose.
Bonus 10 seconds. Message for the audience that is watching this for the first time. They come across this video, say, hey, what is this? Let me listen. And they listen to the whole thing. Message for the audience, StingRay. 10 seconds.
Okay, yeah. Yeah, this, I mean, it got heated because of points sometimes, and people vehemently defend their points, as do I sometimes, or want to jump in there. But I do believe that, I actually do believe there's no animosity between me and Rachie, even though we've got a different view of what the world is. And I even, I even messaged and had a conversation with her about parenting and stuff. We're all human beings. We can have a debate without ridicule, without calling names or shit like that, and just have general discourse. It's really easy, guys.
Thank you, Rachie. Last wrap up, a message for the audience. If anybody is new watching this for the first time, a message for those people.
Okay, like and sub to Jose, and yeah, like StingRay said, there's no I can't even say that word either.
Animosity.
Animosity, yeah, between us. Like, even though sometimes we can get heated and like we can defend our point of view, and sometimes get backed into a corner sometimes and want to say that we're right and prove that we're right. There's no animosity, there's no hard feelings. Like StingRay said, we've talked about parenting and things. He's a nice guy, and there's no bad feelings between me and him at all.
That's good. My message for the audience, if anybody new is watching, and if you're interested in these topics and science and earth and the shapes and math and physics and all this kind of stuff, if you want to argue about a specific point, learn from the mainstream explanation, learn from what you have learned in school, learn it well. If you want to refute it and you want to go against it, if you want to present an alternative to how it works, my best advice for you is learn the way it is now. And once you know the way it works, then you can refute it and come up with an alternative. Thank you very much, everybody. I really, really appreciate your support on watching, liking. Leave a comment in the comment section, please. And make sure that the bell notification icon is on. Rachie 50, thank you. StingRay, thank you. Thank you to all the audience. Jose JG, out. Boom.